Now, shall we start?
Yes.
Good evening, all. Respected distinguished guest, Director Sir, CEO Sir, Principal Sir, Dean Academic Ma'am, teachers, staff members, and participants. It is with immense pleasure and pride that we gather here today for the inauguration of one-week faculty development program on recent advances and applications of manufacturing in industries 4.0. I, Dr. Snehika Srivastava, Co-Coordinator, FDP, on behalf of IPS College of Technology and Management, feel honored in welcoming you all. In this faculty development program, some of very useful yet a bit difficult topic will be dealt. The renowned professor as subject expert from the reputed institutions will be conducting session and giving presentation on chosen subjects. I take this opportunity to extend my sincere gratitude to AICT Training and Learning Academy Scheme, Atal, New Delhi, for granting this program to our institution. I do hope you all will be benefited by the knowledge inputs from the subject experts. Each one of it will be interactive knowledge sharing platform. You have the opportunity to get clarification should you have any gray area. Thank you all for joining us on this occasion. Now let's proceed for the inaugural session. I would like to invite Principal, IPS College of Technology and Management, Dr. Anurag Garg, to present welcome address. It's over to you, sir.
Good evening, all the present members. It is indeed a privilege for me to welcome on behalf of management of IPS Group of Colleges and IPS College of Technology and Management, in particular to you all, in inaugural function of the Faculty Development Program on recent advances and application on manufacturing industries 4.0. At the outset, I feel it is a great honor for us to have Professor V.K. Jain, former professor from IIT Kanpur, who has been gracious enough to accept our invitation to inaugurate this faculty development program. I must also add that presence of all of you in this Atal faculty development program will add immense value to the FDP. We are also pleased to welcome our esteemed speakers who have taken the time to share their expertise with all us. Your insights and knowledge will inspire and guide us through the upcoming sessions. We deeply appreciate the interest taken by all the participants from various organizations to be part of this faculty development program. Your presence and engagement will enrich the discussion and pave the way for meaningful outcomes. This FDP is a testament to the spirit of collaboration and innovation, focusing on advanced manufacturing in Industry 4.0 with the objective addressing global challenges and exploring sustainability solutions over the next 6 days of the FDP. We will witness thought-provoking sessions, insightful presentations, and interactive workshops that promise to stimulate new ideas and collaborations. Once again, I welcome you all. Let us work together to make this gathering a resounding success. Thank you very much.
Thank you, Principal, sir. Now, before start, we all must be briefed about the faculty development program. So for this, I would like to call Dr. Manoj Narvadia, coordinator of the FDP, to present the outline of the program. So please.
Thank you, ma'am. Respected dignitaries, distinguished guests, esteemed speakers, delegates, and participants, a very good evening to all of you. It is my privilege to address you as the coordinator of Faculty Development Program on recent advances and applications of manufacturing in Industry 4.0, being organized by IPS College of Technology and Management, Gwalior, with the sponsorship of Atal Academy. A week-long program aims to equip faculty members with the latest advancement, trends, and applications in modern manufacturing technologies aligned with Industry 4.0, and to bridge the gap between academic learning and industrial applications. The FDP is structured over 6 days with a blend of expert lectures, panel discussion, and online tests. There will be 13 sessions in the evening, 6 to 9 p.m. from Monday to Friday and 2 to 8 p.m. on Saturday. The program features distinguished speakers from academic research institutions with industry, including internationally and nationally renowned professors from reputed engineering institutions, experts from industries, specialists from research organizations focusing on Industry 4.0 technology. The program is designed for faculty members, researchers, and industry professionals keen on advancing their knowledge in modern manufacturing and industrial 4.0 applications. We are delighted to host almost 250 participants from all over India. Their contributions in cutting-edge research, case study, and industry insights. This diversity enriches the faculty and fosters a truly global exchange of ideas. At the end of FDP, participants will gain a comprehensive understanding of Industry 4.0 and its impact on manufacturing, develop strategy to integrate Industry 4.0 concept into their teaching and research, establish networking opportunity with industry and academic experts for future collaboration. The FDP is a significant step towards fostering innovation, skill enhancement, and knowledge sharing in the academic and industry sectors. With the support of Atal Academy, this initiative is expected to contribute effectively to the professional growth of faculty members and researchers in the domain of modern manufacturing technology. Finally, I would like to express my heartfelt gratitude to the organizing committee, volunteers, and sponsors for their tireless effort in bringing this event to life. Their dedication has made this gathering possible, and we are grateful for their support. Thank you.
Thank you, sir, for giving detailed information. Today, we have the honor of inviting a visionary leader, an educator for excellence, and the guiding force behind our institution, our respected director, IPS Group of Colleges, Dr. Arun Kumar Tyagi, to address the audience. So, please.
Thank you. Good evening.
Amen.
It is my privilege to welcome Professor V.K. Jain, who is known all around in the field of research and innovations and has been very kind to this institute always to help us in finding new ways and means to instill the confidence in the students and the teachers. As you know, as Dr. Snehika and the principal of the institute and the organizers, they have just told that recent advances and applications of manufacturing in Industries 4.0, which is being organized by IPS College of Technology and Management under the esteemed sponsorship of Atal Academy. In today's rapidly evolving industries landscape, the advent of Industry 4.0 has transformed traditional manufacturing paradigms through automation, digitization, and advanced data analytics. The integration of technologies such as the Internet of Things, artificial intelligence, and smart manufacturing is reshaping the way industries operate, enhancing efficiency, precision, and sustainability. This FDP serves as a crucial platform to empower faculty members with the new knowledge and skills that will not only strengthen academic curricula but also bridge the gap between theoretical learning and industrial applications. Through expert lectures, interactive discussions, and hands-on sessions, we aim to equip our educators with insights into the latest technological advancements and research prospects in this domain. I extend my heartfelt gratitude to Atal Academy for their support in making this event possible. I also appreciate the efforts of our esteemed speakers, organizers, and participants whose commitment and enthusiasm will undoubtedly contribute to the success of this program. I request all the participants to actively engage, exchange ideas, and leverage this opportunity for professional growth and academic excellence. Let us work together to shape the future of manufacturing and innovation in Industry 4.0. Wishing you all a fruitful and enriching learning experience. Once again, before I close, I extend my warm welcome to Professor V.K. Jain.
Thank you.
As and when there is a talk of, manufacturing, mechanical engineering, whatever it is, and Dr. V.K. Jain is the most suited person for that. So, sir, Again, welcome you.
Thank you very
Thank
much.
you all.
Thank you, sir, for your motivating words, which are always inspiring for us. We are privileged to have Professor V.K. Jain, former professor, IIT Kanpur, among us, and we eagerly look forward to the words of wisdom and insight he will share with our audience. But before his speech, I take this opportunity to present bio-sketch of Professor V.K. Jain. Dr. Vijay Kumar Jain passed his BE from MACT Bhopal in 1970, ME and PhD from University of Roorkee in the year 1973 and 1980 respectively. Sir has 47 years of teaching and research experience. He has served as a visiting professor at the University of California at Berkeley, USA, and University of Nebraska at Lincoln, USA. Professor Jain retired as a professor from IIT Kanpur. He has also served as a faculty at other Indian institutions. Dr. Jain has won 3 gold medals, 2 silver medals, and Best Paper awards as recognition to his research work. Dr. Jain has written 9 books and 16 plus chapters for different books published by international and national publishers. Sir has been awarded Lifetime Achievement Award by the AIMTDR NEC. Dr. V.K. Jain is presently as editor-in-chief for 3 international journals and associate editor of 2 international journals. Sir has also worked as a guest editor for 22 plus special issues of different international journals. He has been opted as a member of the editorial board of 12 plus international journals. Dr. Jain has guided 20 PhD, 100 plus MTech, and 30 plus BTech while working at different university during his career. He has 400 plus publications to his credit. He has 13 Indian patents and 1 USA patent on his credit. His experiences and expertise promise to leave an indelible mark on our heart and minds. So please join me in giving a resounding and heartfelt welcome to our guest of honor, Professor V.K. Jain. It's over to you, sir.
Thank you very much, Dr. Snehika Srivastava. I want to thank organizers of this FTV, Director of IPS, Principal of IPS, and Professor Manoj Narwaria, Dean R&D and Professor in Mechanical Engineering Department, in particular, for inviting me to inaugurate this faculty development program. I, on my personal behalf, welcome you all to this faculty development program on the theme Recent Advances and Applications of Manufacturing in Industry 4.0. I will be basically, which is being organized by IPS College of Technology and Management, Gwalior, at virtual mode from 3rd February to 8th February 2025. I will not talk about Industry 4.0. You will be hearing a lot during the program. But I will like to mention manufacturing is a wide and very important area for all countries across the globe. Many of us are familiar with the fact that at one point of time, say 3 to 4 decades back, we used to buy everything made in Japan. My simple question is why? They were excellent in manufacturing of different categories of products. That's why we all wanted to buy the things from made in Japan. Nowadays, you go to the markets of USA, America, United Kingdom, France, Germany, Singapore, and for that matter, anywhere, you will find that a large number of the products that you are purchasing there are being sold in the market of these countries, but they are made in China. The simple question is why this trend has changed from Japan to China. The question arises, why such a change? The quantum and quality of R&D that is research and development activities in general, and R&D budget of that country in particular makes a big difference. I hope the director and the principal of this college will agree with this my point of view. USA at present, I searched it yesterday on Google. USA is spending as billion US dollar 760 per year on R&D. China billion 620 US dollar. Japan just 180 US billion dollar. Germany 132. And unfortunately, India does not appear anywhere in the top 10 countries, maybe even top 20 countries. India's R&D budget is, I hope you will be surprised to know, is around less than 55 US billion dollar, while China has 620 and USA has 760 billion dollars. So you can compare how much we are spending on R&D budget as a whole country. Hence, you can imagine where our country stands with reference to R&D budget at the global level. Please don't mind it, but these are the facts about the country. So we should be able to imagine where we should stand in R&D. Doesn't matter manufacturing or ship making or IT, whatever it is. When we want to talk of manufacturing, we have to be very careful regarding not only meso and macro manufacturing, because most of the lectures you find here as well as in other faculty development programs, they are just dealing with meso or macro manufacturing. It should also include, in my opinion, very seriously, micro, nano, and not only nano, sub nano manufacturing, which are normally ignored in such programs and frankly speaking in R&D across the country. These days, you cannot have high level devices without micro nano products in it. You see the various devices around you while sitting in this program itself, say laptop, mobile, speaker, etc. All of them are having micro nano products for transmitting the things. It does not matter whether it is mobile, laptop, car, aeroplane, all automobile, each one of them have a good number of micro nano devices for their operations. It is good to see in the list of this FDP program of lectures of this course that a couple of lectures are there which are relevant to micro nano manufacturing. So we should concentrate on just not delivering the lecture, on real time micro, nano, and sub nano manufacturing research. Another important point, please don't, I am not criticizing FTP, I am giving you the facts, so please don't mind it. Another important point that we should keep in mind while organizing such courses on advanced manufacturing is that manufacturing does not mean only machining. Because if you see these lectures, most of the lectures are on machining only. It also includes macro and micro level forming operations, welding operations, casting operations, and many hybrid machining operations or hybrid manufacturing operations and processes like electrochemical grinding, electric discharge grinding, electrochemical spark machining or electrochemical discharge machining, etc. All such topics should be included in such types of faculty development courses, because I know it is very difficult to find the experts to deliver the lectures in these topics. But faculty members should be trained in these areas. Then only they can teach the students in the classes with these topics. However, I can understand the limitations of time and availability of the faculty members of such programs. From that point of view, your FTP program is well planned program. In future, I hope you will have at least one lecture on smart macro micro manufacturing also, as was mentioned in the earlier talk by organizing professors. With these remarks, I wish a successful faculty development program being organized by IPS College Gwalior, which should be beneficial to the faculty members as well as to the students if they are attending it. So, thank you once again for making me a part of this program. Thank you.
Thank you, sir, for gracing us with your presence and sharing your invaluable insight with us. Your words will undoubtedly leave a lasting impact on all of us. Now, I invite Mr. Vineet Raj Singh Kushwa, Organizing Secretary of the 6 Days FDP, to propose vote of thanks.
Thank you, ma'am. Good evening, everyone. I, Vineet Raj Singh Kushwa, on behalf of the organizing committee of the 6 Days Faculty Development Program on recent advances and applications of manufacturing in Industry 4.0, extend my most sincere thanks to our chief guest, Professor V.K. Jain, former professor, IIT Kanpur, for sparing his precious time and gracing the program with his presence. We are fortunate enough to have such a distinguished personality with us. Further, I pay my gratitude to Honorable Director Dr. Arun Kumar Tyagi, Working President Ashwini Mishra, Chief Administrative Officer Mr. P.K. Ghosh for the continuous encouragement for such programs. I acknowledge my gratitude to Dr. Raghar, Principal IPS College of Technology and Management, and Dean Academics Dr. Jyoti Mishra for the guidance and support and making it convenient to organize this program. I would like to mention all my thanks to all the heads, faculty members, staff members who directly or indirectly supported in this event. I must not forget to thank all the participants who patiently attended the program. Thank you all once again.
Thank you, sir. So now we are proceeding for first session of this faculty development program. We are privileged to have Professor V.K. Jain, former professor IIT Kanpur, with us. I invite Professor V.K. Jain to deliver his talk on ECM and anode shape prediction and tool design in ECM. Sir, it's over to you, sir.
I hope you will help me in bringing out my PPT on the screen.
Sure,
Let me
sir.
try. Uh, share screen, right?
Yes, sir, please.
I should click here.
I think actually your screen, yes, now it is visible.
Huh?
Yes, yes, sir, it is visible.
Is it visible?
Not your PPT, yes, but
This is my PPT. Visible?
yes, now your PPT is visible.
Yes, sir.
So I will make full screen, right?
Right, sir.
Sure.
So just I will take a couple of minutes, just a bit. Can you hear me?
Yes, sir.
So I am going to talk about ECM and anode shape prediction and tool design in electrochemical machining. Now, if you have any question, you can raise the hands and ask me. So I welcome to the faculty development program on recent advances and applications of manufacturing industries 4, being organized by IPS College of Technology and Management, Gwalior, during 3rd February to 8th February 2025. Now, my talk is organized as follows. Part 1, it deals with introduction to electrochemical machining. Part 2, it deals with tooling design in ECM, where I am going to discuss about anode shape prediction. Anode means workpiece shape prediction during ECM, and there are various approaches of anode shape prediction. In ECM, those approaches I will discuss, like cos theta method. After that, anode shape prediction, I will discuss the tool design also, that is cathode design and cos theta method for tool design, correction factor method for tool design, and so many others are there. Part 1, introduction to electrochemical machining in brief, because electrochemical machining is a big chapter. I will introduce in brief, and more important thing is, in each place, at each place I have raised certain questions which will be very helpful for MTech and PhD thesis topics. Material removal in ECM, inter-electrode gap evaluation in ECM, single equation for inter-electrode gap evaluation in ECM, self-regulating feature of ECM, chemical equivalent of an alloy, maximum permissible feed rate in ECM, and finally temperature gradient and electrical conductivity evaluation in electrochemical machining. I am not going to discuss it as in the class. There will be in every sheet or PPT some questions, so you have to be careful for those questions. Electrolytes used in ECM are like acidic, alkaline, neutral. Now, as you can see here, this is the electrochemical machining showed schematically. Here is the cathode, that is the tool, and feed is being given towards the workpiece. This is the workpiece, that is the anode, and here you have the electrolyte, not the dielectric. Please be careful. It is not dielectric, it is the electrolyte, which is normally used as sodium chloride solution, but there are so many other electrolytes also. Now, during the electrolysis process, tool is connected to the negative terminal, workpiece is connected to the positive terminal, and you have ferrous hydroxide, ferric hydroxide being produced. And you can clearly see in the next slide, hydrogen ions, hydrogen bubbles are moving towards the workpiece, and oxygen bubbles are moving towards the tool. And there is a very small inter-electrode gap. Normally, it is less than 1 millimeter. Very high, 20 to 30 meter per second, and you have metal dissolution from the workpiece. This is the workpiece material. You can see here positive ions convert as hydroxides, ferrous or ferric in case of iron as anode workpiece material. You can see here, this is the ferrous hydroxide, this is the ferric hydroxide. Inter-electrode gap is less than 1 millimeter and voltage is 8 to 20 volts. And you can see here hydroxides are formed. This is the ferrous hydroxide, FeOH twice, and this is ferric hydroxide. Now, all this process is based on Faraday's laws of electrolysis. Now, here gases H2 and on anode and O2 on cathode are generated. Here, heat is generated due to the electrochemical reaction. Now, it is very important. Generation of hydrogen and oxygen, heat generation, we will discuss them in detail. An electrochemical reaction that is taking place here. Now, this is the equation with the help of which you can find out the material removed. In time t, t small t is the time, I is the current, is the electrochemical equivalent of the workpiece material, that is this workpiece material, this workpiece material. Material removal rate can be obtained using this particular equation. You divide both sides by time t. You can have m by t is equal to m dot is equal to IE over F, where F is the Faraday's constant. Now, material removal in ECM is given by this particular equation, V minus delta V K over YA into E over F rho A, where K is the electrolyte conductivity, delta V is the over potential, YA is the inter-electrode gap, E is the electrochemical equivalent, F is the Faraday's constant. Now, very important, here the question arises, whether the over potential is constant, this over potential, is it constant or it is varying? If not, then on what factors it depends? No book, no research paper deals with this. You can very well find out what are the factors which are going to control and develop the model. Whether the electrolyte conductivity K is constant during the experiments, here K. This is very important factor, electrolyte conductivity, whether it is constant during the experiment or it is varying. If varying, on what factors it is varying? If not, on what factors it depends? So let us see. K depends on temperature of electrolyte, and I have already mentioned it varies during the process. How to determine it in the interelectrode gap during machining? That is another important question. Gas bubbles of hydrogen and oxygen, both of them are going to affect the value of K. Third thing, which is very important also, sludge formed during the machining, because we have seen ferrous hydroxide and ferric hydroxides are generated during the process, and they are going to affect the value of K. Now the question is for all of you, how to account for their effects on linear material removal rate, MRRL evaluation. Do we have models for accounting their effects? Yes, for some of them we have the models, I will show you. Let us discuss these issues during this talk. Without accurate evaluation of these parameters during machining, you cannot accurately design the tools for ECM, and you cannot accurately predict the workpiece profile after ECM. So you can see here, this is the tool we have seen in the earlier figure also, and this is the kind of the cavity being formed by the tool during electrochemical machining. This is the top view. Now note here, MRRL is in the front gap only. Here when we are calculating this MRRL, this is in the front gap. This is the front gap, and side gap is between this wall and this surface being machined. Side gaps are not considered in this particular figure or in this particular equation at present. Now there are two situations. Inter-electrode gap evaluation. What is inter-electrode gap evaluation? If you go, the gap at the bottom of the tool and top surface of the workpiece which is being machined. Now very important thing you see here, tool, it may have zero feed rate, it may have finite feed rate. When zero feed rate, continuously inter-electrode gap is varying, or finite feed rate, still inter-electrode gap is varying. Let us discuss them. For zero feed rate and finite feed rate, we are having separate equations as we will discuss. So my question is, why to have two equations? It creates confusion. Can we have a single equation for both zero and finite feed rate? I will try to answer this question. We have done some work at IIT Kanpur in this direction. Inter-electrode gap evaluation in electrochemical machining. Now let us first consider zero feed rate. When feed rate of tool towards workpiece is 0, case 1, F indicates the feed rate. Substitute F is equal to 0 and solve for by. We get dy by is equal to C dt, where C is the constant. We have already seen the equations in the earlier slide. Integrate both sides and solve it. It gives y is equal to y0 square plus 2ct under root. Now, since feed rate is 0, there is no feed rate term, and this is the parabolic equation, as you will see. Y is equal to y0 at t is equal to 0. T is equal to 0 means machining time is 0, so initial interelectrode gap is y0. This equation is well represented by the figure in the next slide. Assumptions. Now, while evolving this particular equation, there are certain assumptions. K is constant in the interelectrode gap. Very important. I have highlighted this. We will discuss it in detail. Delta V is a small fraction of voltage V, but we do not know exact value in general. K of workpiece and K of tool are considered to be very, very large of electrolyte compared to the electrolyte. That means we are not considering this in the equations that we are deriving for it. Again, this is the simplification. Now let us consider plain parallel electrodes machining is normal to the feed direction. I will show you this. Electrolyte properties are unchanged in z direction, because when we are considering 2D electrochemical machining, then the third dimension, that is z direction, is considered to be unchanged. This equation yields the relationship between interelectrode gap and machining time. Now, as I showed you the equation in the earlier gap, y is equal to certain term under root. So now you can see here, this is the initial interelectrode gap at t is equal to 0. This is y0. And then how it is varying with time t? That is parabolic in nature. That means if feed rate is constant 0, if feed rate is 0, then the interelectrode gap is going to vary. Why is the interelectrode gap? Just like in a parabolic condition. At any time t is equal to 0, that is initial interelectrode gap, the relationship y is equal to y0 follows a parabolic curve. This is the interelectrode gap and this is the time t. Now, in real life electrochemical machining, we do not have zero feed rate, we always have finite feed rate. That means F is not equal to 0. When the parameters are not non-dimensionalized, the solution obtained can be, okay, before that let us see. Here time t, F is feed rate, but this is the equation. T, when the parameters are non-dimensionalized, the solution obtained can be written like this. I am not deriving it. They are given in the books. You can easily see it. T is equal to 1 by F by 0 minus by T plus by E ln natural log by 0 minus by E over by T minus by E. So here important thing is this equation can be solved by iterative process. This is the biggest drawback of this particular equation. Iterative procedure for solution of this equation can be followed because it has y on both sides when you are solving it for interelectrode gap, because our interest is in interelectrode gap y or yt at time t. T is here, t is here. and each iteration takes 30 to 40 iterations for solution at each point may be required. There are hundreds of points in the interelectrode gap and you need 30 to 40 iterations. Computer time when solved, say, for 1000 points will be enormous, especially when using finite difference method, finite element method, or boundary element method. Hence, an explicit equation to evaluate interelectrode gap IEG for both the cases f is equal to 0 and f not equal to 0 without requiring iterative procedure has been proposed by Jain and Pandey. This was done by me when I was doing my PhD at University of Roorkee, now IIT Roorkee. So I will show you this equation in place of using this equation and earlier parabolic equation. You can use this single equation for both the cases, zero feed rate and finite feed rate, and it will save lot of your computer time and it gives you accurate results as given by these two equations 3a and 4a. Now you can see the reference of this particular equation has been taken from electrochemical machining by J. A. McGough, Chapman and Hall, London. Now let us see single equation proposed by Jain and Pandey for interelectrode gap evaluation in electrochemical machining. Let us make the following assumptions. While deriving this equation, following assumptions are made. J, that is current density, remains almost constant within a small area of an element. Now, please, you know it if you know finite element or finite difference. This small area is very, very small. It depends upon you whether you take 1 millimeter element size or less than 1 millimeter element size or larger than 1 millimeter element size. It can be 2D case or it can be 3D case. Computational machining cycle time delta T, which was taken as T in the earlier two equations, parabolic equations and the equation proposed by McGough, is very small such that J, that is the current density during that period, that is delta T period, is more or less constant, important for numerical analysis of this particular process. So you can see here we are taking very small element, so the current density will remain constant in that element during a very small period, that is cycle time t. It can be 1 second or more than 1 second depending upon how big is your problem to be solved and how big is the capacity or and speed of your computer or laptop. So equation for evaluating interelectrode gap for numerical analysis of ECM process, we know this dy over dt. Y is the interelectrode gap, t is the time. How this is varying? This equation E into B minus delta V over F rho A Y into K minus F is the feed rate. Now please note it carefully. I have explained E F rho A, anode density, F is the feed rate and K is the electrolyte conductivity. So it can be written at Ej over F rho A minus F. So you can solve this equation dy is equal to Ej over F rho A minus F into dt. Integration of both equations would give, both sides will give you this equation. Not equation, both sides will give you this equation. Y is equal to C dash minus F into delta T K dash. To evaluate the value of integration constant K, please note it, K dash or K, this is the integration constant, and where C dash is equal to Ej over F rho A. At time t is equal to 0, y is equal to y0, k dash becomes y0. It's constant k dash, this one. Substitute this value in above equation. So you will get this equation converts to y is equal to y 0, that is the initial interelectrode gap, plus c dash minus f into delta t. Delta t is a very small time, as I mentioned. You can take 1 second or more than 1 second. C dash is the constant and f is the feed rate. So you can have zero feed rate here or finite feed rate here. Since t is very small time, hence t can be written as delta t, that has been written over here as delta t. During tooling design for ECM, this equation can be used in place of the two equations discussed already, especially the iterative equation and parabolic equation. Now, so you can clearly appreciate that this particular equation is going to save lot of your computational time when you are using the finite element method, finite difference method, boundary element method, or other numerical method to solve the problem. Self-regulating feature we know, I think many of you may be knowing who know ECM, electrochemical machining, that by the interelectrode gap, in this figure y dash is equal to 1 indicates equilibrium condition. Here when this is having 1, that means it is under equilibrium condition. If it is not under equilibrium condition, then it always attempts to attain the equilibrium condition. As you can see here, at high value of y, it is slowly moving with time and trying to attain the equilibrium condition. And this feature is known as self-regulating feature of electrochemical machining. MRRS, linear material removal rate, V minus delta V, K over Y, E over F rho A, where K is the electrolyte conductivity. We have already seen chemical equivalent of an alloy, because if you are not using the pure metal, then you will be using the alloy, and alloy have more than one metals or materials. So you should know what is the chemical equivalent of the alloy, because we are going to use it here. E is the chemical equivalent of the workpiece material. So if it is an alloy, you should know it, what is its value. A large number of materials being machined by ECM process are alloys, not only pure metals. So the value of chemical equivalent of an alloy can be evaluated by one of the following two methods: percentage by weight method and superposition of charge method. Now the sum of the chemical equivalents Ai over Zi of each element I indicates the element, A is the atomic mass, and Z is the valency, in the alloy is multiplied by its respective proportion by weight Xi in the alloy. It gives a value for the chemical equivalent of the alloy, where n is the number of constituent elements in the alloy, because it may not be one or two elements, maybe more than one element. So n indicates the number of the elements in the alloy. Use this value of E is equal to AYZA in the equation of MRR that we have already seen in the earlier slide, MRR equation. For the dissolution of 1 gram of alloy, the total amount of electric charge required for dissolution by individual element is equated to Z over A small a indicates alloy, capital A indicates atomic mass, and Z indicates valency of that particular alloy A, the alloy element A. F indicates F coulombs into multiplied by F. So this is the equation for percentage by weight method. A by Z, A is equal to 1 over 100, I is equal to 1 to N, AI over ZI, XI. This is for the percentage by weight method, and this is for the superposition by charge method. Z over A, here also you are finding out A over Z, here Z over A. So you can see this particular equation. I, as I have already told you, indicates N is the total number of elements, I is the ith element. Or you can write it in this terms, A over ZA is equal to 100 divided by summation I is equal to 1 to n xi zi over ai. So this is how you can find out the chemical equivalent of an alloy by percentage by weight method or percent superposition of charge method, and both give different values. So you have to compare the MRRL obtained with this method and with this method, and then select the one which give nearer values. Now this is very important part in this particular talk. Electrical conductivity, temperature gradient, and current density evaluation in ECM. Electrolyte conductivity evaluation in ECM, we will see it. Inlet temperature. Now please note it, this is well known equation. It is given in the almost all the books which are dealing with the electrochemical machining. K is the electrical conductivity of the electrolyte. K0 at any place or at any location, we will see. K0 is the initial at the entry point. Alpha, this is the inlet temperature T0. It is the temperature at the point under consideration, and alpha is the constant. Conductivity at any desired point, conductivity at the entry to the interelectrode gap, and this is the temperature coefficient of specific conductance. So you know this equation, I think all of you know it. Here only temperature effect is being considered. Now this is very important that here in this equation only temperature effect is being considered, and large number of researchers and users are using this simple equation, which is not very right. And in the class also many teachers just show this particular equation, that is not very correct, because here we have neglected two factors. One is the hydrogen and oxygen gas bubbles, and second is the sludge formation. So both of them going to affect the value of K. Now here I have raised the question, what about size effect of voids? Now this is very important. You can do your master thesis and PhD thesis even today on this. What about the size effect of voids, hydrogen bubbles and oxygen bubbles, how they are going to affect the value of K? And what about voids and their size distribution effect on K during the interelectrode gap? I don't think anybody has considered this part across the globe on the conductivity. You can do MTech and PhD thesis problems on this particular topic. What else you can do further? That you have to see. What about the sludge effect on conductivity? No papers had done it. Model among this, you can model random distribution of voids in the interelectrode gap, cathode and anode, and you can develop a model, and then you can find out the effect of random distribution of voids in the interelectrode gap on the value of K, and finally on MRRL or MRR volumetric V. Model random distribution of sludge in the interelectrode gap, find N and N dash for different electrolytes and workpiece material. I will show you. Accounting for voids, gases evolve in the electrolyte. The above equation can be modified. Above equation means earlier slide equation can be modified like this. K is equal to K0, 1 plus alpha delta T. This we have already seen. And into 1 minus alpha V, where alpha V is the void fraction raised to power n. And this is what it says, that find the value of n and n dash for different electrolyte and workpiece material, because this is for a particular electrolyte and workpiece material. This value will change with change in the electrolyte. This is the exponent. This is the white fraction, which is less than 1. Now, this work was done at IIT Kanpur by Ankit Kumar Chokse in 2017. Here, here I told you that sludge effect is not being taken into account. So he accounted for the sludge effect and he made this, modified this equation as k is equal to k0 1 plus alpha delta t into 1 minus alpha v raised to power n, this is for void, into 1 plus minus alpha s raised to power n dash. Because sludge may increase the electrolyte conductivity, it may decrease the electrolyte conductivity. So you have to see what material is forming the sludge. This is ferrous hydroxide, ferric hydroxide. It will depend upon the workpiece material. If it is not iron, some other material, then you have to find out how it is affecting the conductivity, whether increasing conductivity or decreasing conductivity. Accordingly, you have to choose this value plus or minus. Here alpha, alpha b and alpha s are coefficients and n and s are exponents. They are derived by conducting experiments, but will change by changing electrolyte, workpiece, material, and tool material. You can see details in this particular reference. Now, temperature gradient evaluation is another very important point in ECM. Temperature gradient along the electrolyte flow direction can also be evaluated from the fundamental equation as follows. This is written from the law of conservation of energy. We can write heat generated is equal to heat dissipated. I think all of you know this. And you can see here, this is the tool, this is the workpiece. Feed is being given, that is tool is moving toward the workpiece by the inter-electrode gap, width of the workpiece. V is the velocity, not the voltage. V is the velocity of the flow of the electrolyte. This is x axis, this is y axis, and heat produced in this particular inter-electrode gap is I square R, where I is the current flowing between the tool and workpiece through the electrolyte, and R is the resistance of the electrolyte. And this can be written as V minus delta V whole square divided by R. Here R of tool and workpiece are neglected. This I have already mentioned to you in the earlier slide also. And this can be written as V minus delta V whole square into K divided by Y over A, where heat dissipated this is the heat generated. Heat dissipated is rho E W by V C E into delta T. Heat dissipation is in the electrolyte. Electrolyte density rho E, width of the workpiece or the gap, this is shown here. Y is the interelectrode gap shown over here. V is the velocity shown over here. C is the specific heat of electrolyte, and delta T is the change in temperature. V is electrolyte flow velocity. This V is the voltage. Please don't get confused. And this V is the electrolyte flow velocity, or this V is the electrolyte flow velocity. Heat produced, heat dissipated, we know it. So you equate these two equations, that is this equation to this equation, that is what you get over here. So from here you can find out delta T is there, dx is there. So you can write dt over dx is equal to this particular equation. All these things can be considered constant, and you can write A multiplied by K. K is the conductivity of the electrolyte, which is varying from point to point. So V minus delta V, rho E V C, and Y can be taken as non-varying or constant for a short period of time, delta T or dt, and for a small distance or element size dx. Now please note it, this has been derived keeping in view that you are using numerical analysis for the solution, that is finite element, finite difference, or boundary element. That's why everywhere you will find short time dt, short distance dx, and short uh, this delta t. Here k, small k, this will be small k, varies substantially with temperature. Hence, it is taken as a variable. K is varying with temperature, K is varying with void fraction, K is varying with sludge concentration. So that we have already discussed in the earlier equations. As in the previous equation, temperature gradient is a function of K, that is the electrolyte conductivity, whose equation has been derived in the various previous slide without accounting for void fraction. Later on, we accounted for void fraction as well as sludge both. So this is written dt over dx is equal to a k0 1 plus alpha delta t. T0 to T. T0 is the initial temperature at the entry, and T is the temperature at the point where we are considering, or maybe at the exit. dt a k0 0 to x 1 plus alpha t minus t0 into dx. From this equation we can write this. Solution of this equation results in t minus t0 is equal to 1 over alpha exponent alpha a k0 x minus 1. Please note it carefully. Here in this particular equation, only the effect of temperature is accounted for. They have not considered the effect of void fraction as well as sludge. So it can be a very good research problem to find out how void fraction and sludge are affecting the temperature variation inside the interelectrode gap. Substitute the value of K in this equation as derived earlier. The current density J varies along the gap because interelectrode gap is varying along the flow direction. So definitely current density will vary, and it can be evaluated as follows. V minus delta V K over Y. If you substitute the values, V minus delta V over Y into K, value of K, if you substitute, it becomes K0 1 plus alpha delta T, that is T minus T0. So from here you can find out the current density. Substitute the value of T minus T0 in this equation as derived earlier, that is this one. So you can get this particular equation for current density also. So now we are very clear. You can find out the temperature gradient, you can find out the effective electrolyte conductivity, you can find out the current density. However, current density, this equation takes only the effect of temperature, not the void fraction and the sludge. So you can very well do your MTech or PhD using this particular issue. Now let us move, after having some preliminary knowledge of electrochemical machining, let us see what is tooling design in ECM. This is very, very important, and it has affected the accuracy of electrochemical machining on the shop floor to a large extent. Anode means workpiece shape prediction. There are various methods. For this, various researchers have proposed various methods. One of them is cos theta method. Another is conducting paper analog method. Production Engineering Research Association UK also proposed a method. Empirical approach, we will discuss it. Nomographic approach, I will discuss it. Complex variable approach was also proposed. And finite difference method as well as finite element method. I proposed this finite element method in the year 1977-78 to applied it to the electrochemical machining process first time. Then boundary element method is also there. This work was done at University of Manchester, England. Now this is very important, tool design or cathode design. Again, there are various methods like cos theta method, complex variable approach, finite difference method, finite element method was done first time at IIT Kanpur. I will detail this out. Boundary element method. Correction factor method for tool design was again proposed by IIT Kanpur sometimes back. We will discuss it. Right? So here I will emphasize on these three things. Finite element method, correction factor method, and first time it was proposed by IIT University of Roorkee when I was at University of Roorkee, and IIT Kanpur when my students applied it. Now, tooling design means two things: anode shape prediction and tool design or cathode shape prediction. Cathode shape design. The analysis problem deals with the prediction of work profile obtainable from a given tool. That means tool shape and size are given to you while operating under the specified machining conditions. So the machining conditions are also given to you when you are attempting to predict the anode shape or the workpiece shape. And this is known as analysis problem. When we are talking of cathode shape prediction or design rather than prediction, design problem. The design problem deals with the computation of the tool shape and size which under specified machining conditions would produce a workpiece having a prescribed shape, size, accuracy, and sufficiency. So we are always concerned with the workpiece shape, size, accuracy, and sufficiency. So we should be able to design the tool which will give you the desired workpiece characteristics. Now this has been taken from the reference of Jain and Rajurkar, an integrated approach for tool design in ECM. This was published in Precision Engineering. Now this is important figure. Please try to see it. This is the workpiece. This is the tool. Electrolyte is flowing. This partially coated here. A0 is here at the entry side. This is the side surface. This is the front surface. This is the stagnation zone. This is the front. This is the transition zone. This corner corresponding workpiece surface is the transition zone. If you take the cross section across AA here, then you will get this shape of the workpiece and the tool. Now here, zone 1 is the stagnation zone. This is the stagnation zone. Zone 2 is the front zone. This is the front zone. Zone 3 is the transition zone. This is the zone corresponding to the corner of the tool. This is the transition zone from here to here. And rest is the side zone, that is the zone 4. Divide the machining zone in a number of parts wherever irregularity is there. So this you have to keep in mind to understand rest of the lecture. Now, you can have the bare tool for drilling operation. Here I am explaining it with the help of the drilling operation. So this is the kind of the side you are going to get on the workpiece surface. This is the front side. If it is fully coated or insulation layer is there on the tool, coated tool, then you will get the straight sided profile of the drill hole on the sides, and this is the front gap. So you can clearly see the difference between the bare tool and the coated tool, which are going to give different shapes on the workpiece. Anode shape prediction in ECM. What is anode shape prediction in ECM? Consider the case of electrochemical drilling for understanding the process of anode shape prediction. You are given the following points: inputs, machining conditions like voltage, etc., electrolyte flow pressure or electrolyte flow velocity, electrochemical equivalent of anode material. Tool, yes, while predicting the anode shape, you are given the tool profile, x, y coordinates of tool if it is 2D, or x, y, z coordinates of the tool if it is 3D. Now, using a particular method, heuristic, finite element method, finite difference method, empirical, etc., calculate the interelectrode gap at different points along the tool axis. This we have seen in the figure, earlier figure, that interelectrode gap is calculated. Finally, these points should be joined to get the obtainable anode profile. I will show you. Say, let us take the plane parallel machining. This is the tool. This is the workpiece. Now, please note it is for zero feed rate. That means tool is stationary. It is not moving towards the workpiece. At time t equal to 0 means before starting the machining. This is the internal. U is the velocity, T0 is the temperature at the inlet, electrolyte flow velocity, T0 initial temperature, and T1 is the final temperature. Now you can see this gap is increasing as you are moving in the direction of the flow of the electrolyte. Now here it was here Y everywhere. Here you can see Y1, Y2, Y3, and temperature here T0. Here it is T1, and this has become slanted because material has been removed from this. Now the question is why it is slanted, because as you are moving in this direction, temperature of the electrolyte is increasing because of heating of the electrolyte. And if temperature increases, then electrolyte conductivity is increasing. These are the calculated theoretical results. Here we are not taking into account the voids and the sludge. So you are getting this straight sided slanting temperature. Y3 is greater than Y2 and Y2 is greater than Y1. And this is at T is equal to 50 seconds. Now, if you increase it to 100 seconds, this has further gone down. Workpiece has further increased. This gap has further increased here. It is shown again by 3, by 2, by 1, but these by 3 and this by 3 are different. And this is the amount of material that has been removed from here. So you can clearly see that if you calculate the interelectrode gap at different points, you join them, then you can predict the shape of the workpiece. And this is for plain parallel electrode machining with zero feed rate. Please note it carefully. That's why this gap is continuously increasing. This is the amount of material removed. Note, tool remains stationary. Tool is not moving here, here, here. They are stationary. But workpiece is moving down due to the removal of the material. As you can see, workpiece has moved from this position to this position continuously. Now, let us consider it an example of tool design for plain parallel electrochemical machining for finite feed rate. Now this we are considering for finite feed rate. So this is the tool. This is the workpiece, same as in the earlier case. Here feed rate is F1. U is the electrolyte velocity, flow velocity and temperature. And this is at T equal to 0 second. Now at T 50 second, this is the interelectrode gap by 1 by 2. Now since tool is also moving, so it is not, this difference is there. Here it is more, here it is less. But initial gap is being more or less maintained at the inlet. But it is increasing as you move away from the entry point. Tool feed F1 millimeter per second at 50 seconds. T1 is the final temperature over here. So you can see here, initial gap, this and this, they are the same. But as you move towards the end exit, it has increased. That means material has been removed. Please don't get confused. Here you are going straight sided plane because we are considering only the effect of the temperature. Other two effects are ignored. Otherwise, in real life, it may not be exactly this. So please note tool shape is given, but workpiece shape is being predicted. Tool shape is given, and this is the final predicted workpiece shape by joining different points over here. Numerical finite element method analysis approach. Use the high speed computers. These are the steps. Decide type of analysis, whether you want one dimensional, two dimensional, three dimensional. Collect initial data. Initial data about the voltage, conductivity, temperature, etc. Perform preliminary computation. Solve finite element problem either as temperature distribution or electric field potential distribution. Then calculate secondary variables such as temperature, distribution, electrolyte conductivity, current density, etc. Then calculate inter-electrode gap that we have shown you in the earlier slides along the electrolyte flow direction. Material removal linear at each node has to be considered. We have already evaluated the equation MRRL. Using the computed inter-electrode gap at different points. There can be hundreds of such points. I have not shown those points in the earlier slides. Make anode profile by joining them. Now you have to assume it as a linear. If it is non-linear, that you have to see if you are not taking only the temperature effect, but the other effects are also being there, then it may come out to be non-linear. Goal to determine inter-electrode gap at nodes on the workpiece, and finally to predict the anode profile. Now here you can see this is for drilling operation. Whatever we have seen earlier, that was for plain parallel electrode machining. This is for drilling operation. It will be more clear. This is the tool, feed is being given. Now these are the inter-electrode gap at different locations. This is the point node 1, node 2, node 3, and so on. There may be hundreds of such nodes on the workpiece. And find out the inter-electrode gap at each node and then join it like this. This is the another side. This is the front gap. This is the transition zone. And this is the stagnation zone if you are supplying the electrolyte through the tool. If not, then transition on this stagnation zone will not be there. So this is anode profile calculation over here. Temperature distribution problem can be solved as use appropriate differential equation, evaluate temperature distribution along the electrolyte flow direction. Differential equation can be solved by finite difference method, finite element method, or boundary element method. From the above temperature distribution, calculate electrolyte conductivity K at different points. Effective feed rate, this is very important. You have to find out the effective feed rate also. It will not be the same at every point. In the side gap, it will be quite different and continuously varying. In the front gap also, as well as in the transition gap also, transition zone also, this effective feed rate will be different. So you have to develop a small program to calculate this. Assumption Ohm's law is followed. Compute current density J at different points. Please note it, this is the assumption. In real life, Ohm's law is not being followed. It is Laplace equation which should be solved. Using J, calculate inter-electrode gap at different points along the electrolyte flow direction. Plot anode profile from inter-electrode gap at different points. I have already shown to you. You can see here, this gap is continuously changing. So effective feed rate, because feed is in this direction, here feed rate will be very different. So you have to calculate the effective feed rate in the side zone, transition zone, and front zone at every point. Limitations. Assumption Ohm's law is obeyed, which is not true. Lines of electric field potential are not always straight and normal to the electrode surface, especially when a curved zone is analyzed. As we have seen in the earlier slide, side zone and transition zone both of them have the curved surfaces. Hence, the solution of Laplace equation is recommended. Later on, I used the Laplace equation long back in the year 1979 or so for solving these problems. Electric field potential distribution. Calculate electric field potential by solving equations in 1D, 2D or 3D. This you can use Laplace equation, which I told you Ohm's law is not being followed. You have to solve this Laplace equation either in 1D, 2D or 3D. And then phi is equal to 0 at the cathode and phi is equal to effective voltage delta V minus V minus delta V at the anode. This should be V and this should be minus delta V. Calculate the current density. Using this equation, dt over dx ak, this we have already seen how to derive it. Find temperature at different nodes or points and use it to modify the electrolyte conductivity, because electrolyte conductivity is function of the temperature, and so in those elements you have to separately solve it. Compute current density at different points, compute interelectrode gap at different points, connect these interelectrode gap points and predict the anode shape like this. These are the different points. Calculate interelectrode gap and then connect all these points to predict the anode profile in case of electrochemical drilling. Flow chart for anode shape prediction. Procedure using FEM. Start, read given data and print input data. Generate nodal coordinates. Generate stiffness matrix. Compute number of computational cycles. Compute feed rate in different zones. We have seen the curved surfaces are there in side zone, transition zone, front zone, as well as stagnation zone. Apply boundary or initial conditions. Solve equation to evaluate potential or temperature at different nodes. We have already seen Ohm's law as well as Laplace equation. Compute change in electrolyte temperature. Compute electrolyte conductivity. If feed rate is 0, yes, compute Y for 0 feed rate. If feed rate is not 0, compute Y for finite feed rate. Now please note it carefully. This was prepared when I was using two equations, but later on I developed single equation. So this may not be required. This part may not be required there. Find current density. Compute linear and volumetric material molet, MRRL as well as MRRV. Reassign Y coordinates for the side flow. Modify V for new value of by triple, that is check if machining cycles are complete. If not, then go to earlier point shown by dollars. Then print the results and then it ends. So this gives you different steps to be followed in anode shape prediction. For each step, you have to develop subroutine and connect with earlier one for extracting the information. Other approaches for anode shape prediction, I will not discuss them in detail, but I will just tell you empirical equations, you can easily do it. These equations are based on the experimental results. A0 is the initial interelectrode gap, RC is the tool corner radius, and with this equation you can find out YE is the equilibrium gap. It should be greater than 0.15 millimeter and less than 0.6 millimeter. And RC is greater than 0.5 millimeter and less than or equal to 5 millimeter. This particular equation is valid. This was proposed by Koenig and Paul, where E star is the Euler number. Now, for the case of tools partially or fully coated, this was for fair tool, partially or fully coated on side wall and having RC greater than 1 millimeter, less than 5 millimeter. RC is tool corner radius. Then Koenig and his group proposed another equation, that is this one. This is different from this one. For these conditions, this is for these condition, and this equation is for this condition. So slight difference is there between the two, where BB is 0 and for Y is this much. This is for BB is equal to 0. This means we are between 0 fully coated one, and this is for BB greater than 1 millimeter. BB is the coating length. Above equations are reported to yield erroneous results at low feed rate. I myself conducted the experiments long back, and I found if feed rate is less than 0.006 millimeter per second, then it does not give correct answers. And large equilibrium gap is greater than 1 millimeter, then also they are not giving good results. So you can refer the paper by Koenig and Paul, published in Annal CIRP, volume 18 in the year 1970. You can see here, this I have already shown to you. Schematic diagram, 4 zones I have already explained to you. Then there was empirical approach proposed by Jain and Pandey in the year 1985 or so. A0, because earlier equations were quite a bit complicated, so we simplified them, and based on experimental results, by plus RC2, where RC1 and RC2 depend on many factors like tool and workpiece material, combination, electrolyte, etc. They are evaluated experimentally. Equations to evaluate AS and AS dash in the side zone, because what Koenig and Paul gave were in the front zone only, but we gave some equations in the side zone also, AS and AS dash in the side zone under coated and bare part of the tool. I'm sorry, this was proposed by Koenig and Paul. This equation, we proposed this particular equation, and he proposed this particular equation. So what I am trying to tell here is, with the help of these equations, you can predict the inter-electrode gap at different locations, combine those inter-electrode gaps, and then you can predict the anode profile, that is workpiece profile. All these equations are given in the reference by Jain and Pandey, published in ASME, American Society of Mechanical Engineers, in the year 1984. Nomographic approach I am not going to discuss because I am lagging behind. Nomographic approach was again proposed by Koenig and Paul in the year 1970. What they have done, they have taken this R as the radius of the tool and here as the inter-electrode gap, and for different, this is the inter-electrode gap AG along the x-axis, and along the y-axis they are given the R, that is the radius of the tool, and they have tried to find out the inter-electrode gap on this particular graph, and this is very good for the use in the shop floor, but the results are not very accurate as desired in the high level or sophisticated industries. You can read it in the book, it is given in there, so I am not going to discuss it in detail. Again, this is given by Koenig and Paul in the year 1970, and it was published in NLCIRP. Now, cos theta method, this was proposed by Tipton. Now, it is applicable when angle between feed direction and normal to the workpiece or tool surface is gentle, means it is not large. This method was proposed by Tipton. It is not applicable in case of sharp corners. Applied for the three regions, theta is 0, theta is 90 degree, and theta something in the following slide I am going to show you. Here phi is the interelectrode gap or equilibrium gap for theta is equal to 0. You can find out interelectrode gap is equal to y over cos theta for theta greater than 0, less than 90 degree. Interelectrode gap is parabolic in case of theta is equal to 90 degree. We have already seen in the very beginning. Cos theta theory is not applicable to regions shown in the figure next, complete sharp corners, etc. Current flow lines are straight, parallel and normal to the workpiece, tool and both surfaces. Now here is the question. I have already told you this question because the current flow lines through the electrolyte are not going to follow Ohm's law, which is this is the assumption it is based on. So one should go for Laplace equation rather than the Ohm's law. But these are simple solutions for the same. Assume stool and workpiece surface uniform in z direction. Let workpiece surface be y equal to fx. Now, when you are assuming this, y is equal to fx, point A on the workpiece transformed to point B on the tool. Y over cos theta from workpiece surface, as we can see here. This is the cathode, that is the tool. This is the workpiece. This is YE, equilibrium gap. This is the slanted surface of the tool, and this is the surface you are going to get on the workpiece. And this is the top surface over here. Here it is 90 degree. Here it is 0 degree with feed direction, and here it is something different. This is the feed direction, and this is normal to the workpiece surface. So this is the angle theta. So it is applicable for all the three conditions, but with certain constraints. Now, this is the equations you can see here derived for this particular one cos theta method. Y minus y1 is equal to AB cos theta. Here you can see here, this is the line AB and this is the angle theta, or this is the angle theta. This is A and this is point B. So using these 2 points in this particular figure, we have derived certain equations in the following slide. And this is the final equation. We already know dy over dx is equal to tan theta. So we will get y is equal to y1 plus ye equal, this is equation from this particular equation. You can see here y is equal to y1 plus ye. So you can substitute it x in this particular equation too. So we get x1 is equal to x plus ye, because this is ye, and tan theta dy over dx, because tan theta is dy over dx. Y is taken as a function of x. So we will get ye plus y1 is equal to this much. Now we can consider workpiece surface can be approximated by a series of parabolic arcs. Whatever you are getting there, you can approximate it by parabolic arc, that is y equal to a plus bx plus cx square. Now from earlier equations 4a and 4b, if you substitute here, because y was equal to y1 plus ye, so this was given in the earlier equation, substitute the values of 6b, this, and 4b, earlier one, in 6a. This is the 6a, because this is parabolic equation. So we will get y1 plus ye, that is y a plus b, x value we substitute here, and c x square is here. So you get this particular equation. You can simplify this, differentiate both sides with respect to x, then one gets dy over dx is equal to a plus ba. Differentiate this equation, so you get a plus sorry, a will cancel out, but when you differentiate it, b plus 2cx you will get from this particular equation. Substitute the value of x from equation 4b, that we have seen earlier, b plus 2c x. Simplify this equation to get dy over dx is equal to b plus 2c x1 over 1 plus 2c by e. So finally we get this. Find substitute the equation, now we get this particular by 1, that is the inter-electrode gap, workpiece displaced by ye, a plus b x1 plus c x1, this was the equation we assumed, minus ye. So this is displaced by ye, and this is the correction factor, minus ye b plus 2c x1 whole square over 1 plus 2c ye. Now in this way we can consider this, and we can consider the case 2 also. Workpiece surface is presented by a straight line. If you substitute the c is equal to 0 in the above equation, then we will get y equal to a plus bx, because there was c x square also. So if c is 0, then that becomes 0. So we get a straight line equation. So y1 is equal to a plus b x1 minus y minus yb square is substitute here. C is equal to 0, you will get this particular equation. From this equation itself, you will get this equation. So a plus b x1 minus ye1 plus b square. Since y is equal to a plus bx, that is given over here. B is equal to tan theta. So 1 plus b square, 1 plus tan square theta. This we know already, so this becomes to be 1 over cos square theta. So substitute this value over here. Y1 is equal to a plus bx1 minus ye over cos square theta. So we can get this. Case 3, three-dimensional analysis. I am not going to deal it in detail, but you can solve these equations. Y is equal to a plus bx plus cx square dz ez square g xz and so on. Second degree equation for 3D. Following the above procedure, the tool shape can be presented by this particular equation. I am not going to deal in detail. It is given in my book also on advanced machining processes. You can look into it. What I am trying to tell here is that you can design the tool, you can predict the shape of the workpiece accurately if you follow tooling design procedures. This is the workpiece surface displaced by A. And this is the correction factor. This is displaced by E, and this is the correct, all of this is the correction factor. I will just quickly tell you the correction factor method for tool design in ECM. So far we have discussed cos theta method. Now correction factor method has been applied by one of the authors at IIT Kanpur, student at IIT Kanpur, Mr. Reddy, long back, using finite element technique for 1D, 2D tool design in ECM. You can follow these steps using the anode shape prediction model based on finite element method. The anode profile is estimated for an assumed tool shape and specified machining conditions. Compare the computed and the desired work shape. And now please note it carefully. Assume tool shape, initial tool you are providing with certain experience, and then you are designing it. So be careful about this. Compare the computed and the desired work shape at every node, and difference between the two is the error at that node. Now, if error is greater than tolerance value, because for every product you are going to make, you always have a tolerance value. So if error is greater than tolerance value, calculate correction factor. Modify the tool shape by applying this correction factor, and then repeat steps 1 to 4 until the desired shape is achieved. And this you can see details in the Reddy MS, Jain VK and Lal GK paper published in 1988 in the tool design for ECM correction factor method. It was published in Transaction ASME, Journal of Engineering for Industry. Now this is the flow chart. Start. Assume the initial tool shape. Predict the workpiece surface. Compare the computed work shape with required work shape and obtain the deviation between the two. Then calculate the error at each node. Each error compare for all is smaller than the tolerance. Yes. Calculate correction factor, modify the tool shape and go here. If no, then stop. Now you can see here. Now very carefully, these are the results obtained using finite element method with correction factor. So see, this is the design tool shape. Okay, before that, let us see. This tool shape was used. This was the used tool shape. This is the design tool shape. And when we were using the design tool shape, this is the experimental work is shown by stars over here, and this is the predicted tool to predict workpiece shape using the design tool. And you can see hardly there is any deviation between the predicted workpiece shape and the experimental workpiece shape when we are using the design tool, not the used tool. So this clearly tells you, and here you can see the difference between this is the predicted tool shape, or sorry, design tool shape, this is a used tool shape, and this is both are matching. So you can clearly see there is the importance of the design tool shape. Check matching of predicted and obtained workpiece shape. Check the used tool and the design tool. Conclusions. ECM theory based on Faraday's laws of electrolysis has been discussed in detail for MRRL, YE, conductivity of electrolyte, temperature, current density evaluation have been discussed. At various stages, what are the potential areas of research for MTech and PhD thesis have been elaborated. This should be very helpful to the researchers interested in working on ECM and tooling design in ECM. We have discussed about tooling design on ECM, which includes anode shape prediction and cathode shape and size design. Various techniques have been used for this purpose, namely complex variable approach, para, numerical approach, etc. Empirical approach, correction factor method, cos theta method, nomographic approach have been discussed in detail. Thank you very much. Hello?
Yes.
Hello?
Thank you, sir. Yes, sir. I'm there.
Is there any question? Please let me know.
If anybody wants, this is then question and answer round. If anybody wants to ask questions, then please raise your hand.
No question, right?
Participants, if anybody wants to ask question, please raise your hand. Okay.
Hello, good evening, sir.
Good evening.
Hello, good evening, sir.
Good evening.
First of all, let me thank you for providing such a great, valuable information regarding the tool design in ECM machining. Sir, here I want to know कि while forming a mathematical modeling,
Yes.
generally we make the assumptions. So, what is the correctness of the model if we are making these assumptions?
That is what I have emphasized at different stages. Whenever you attempt a problem first time, you try to
Yes,
make
sir.
it simplest possible so that you are not discouraged from solving. And as you can see here, I started in the year 1977 I worked
Right,
till
sir.
1980 for my PhD, and one by one, I started removing the assumptions to make this
Right, sir.
complicated. And
Right.
after joining IIT Kanpur and MNREC Allahabad, my students started removing those assumptions, making the problem real life. So whenever you start a new problem, you have to make certain assumptions so that you are not discouraged. "Arey, it cannot be solved." Once you have solved it initial stage, then you start relaxing the assumption so that problem becomes nearer to the real life problem. That's why you will see in every theory, you will find the assumptions. But the researchers after that, she or he, have to remove, means relax those assumptions to make the problem real life.
Okay, sir. So we can conclude that anyhow we have to go ahead, and later on, the model will refine as the technology will evolve or future generation will come. Am I right,
Yeah,
sir?
definitely.
Okay.
So you cannot solve the very complex real life problem at the first stage itself. Otherwise,
Yes, sir.
you nowhere. Even though you may not publish initially, but when you are solving on the table, on the computer or on the notebook, you have to say, "Array, let us make this, the temperature," as I told you in case of conductivity. Void fractions were not considered. Sludge was not considered. Initially, temperature was also not considered. K was taken as constant. Then slowly, temperature was taken into consideration. Then void fractions were taken into consideration. Then finally, sludge was taken into consideration by one of the MTech students at IIT Kanpur. So what I am trying to tell, these assumptions are relaxed slowly as the researchers keep moving. Only difference is at some point, at some lab or some institutions, they are relaxed in a short period. At other places or other institutions, if they are complicated, it takes longer time. That's it.
Right, sir. Right. Thank you, sir. Thank you very much, sir.
Welcome. Any other question?
Anybody else who want to ask question? It's okay.
I don't think they have any more question.
It's okay now. Thank you, sir, for enriching our knowledge. To propose vote of thanks, I invite Mr. Vineet Raj Singh Pushpa, the organizing secretary of this 6 days FTP. So please.
Once again, good evening, sir, and all
Good
present
evening.
here. I, Raj Singh Kushwa, Organizing Secretary, on behalf of the Organizing Committee of the 6 Days Faculty Development Program on Recent Advances and Applications of Manufacturing in Industry 4.0, extend my heartfelt gratitude to our esteemed keynote speaker, Professor B.K. Jain, former Professor IIT Kanpur, for his valuable inputs during this faculty development program. I personally liked it very much. He
Thank you.
explained ECM in such a simplest and effective way. He also gave deeper insights of ECM, such as self-regulating features, temperature gradient evaluation, tooling, design, etc. Your expertise, deep knowledge, and engaging session have enlightened us and provided us with new perspectives that will surely enhance our skills and personal growth. Once again, thank you all the participants for being part of this enriching experience. Thank you, sir. Thank you all once again.
Thank you very
Thank
much.
you, sir.
Thank you.
Thank
Thank
you,
you,
sir.
Jain sir. The feedback link will be given at the end of the today's program in chat box and WhatsApp group. Please fill and submit it by tonight. I repeat, dear participant, the feedback link will be given at the end of the today's program in chat box and WhatsApp group. Please fill and submit it by tonight. It is mandatory for all participants to submit feedback for the attendance purpose. Otherwise, you will be considered absent. It is requested to all participants, please stay online. The next session will be started soon. I repeat, it is
Can I make
requested
a
to all
request?
participants. Yes, sir.
Can I
Yes,
make a
sir.
request? If any participant has any question, he or she can write me an email. Within 24 hours, I normally reply those emails if I am not out of Bhopal. Right? So please, I had written email address on my slides also. You can provide them my email address and I will be more than happy to reply their queries. Thank you.
You, sir.
So participants, the sir's mail ID we will display in chat box also. If you have any query, if you want to ask any question from the sir, you can mail to the sir. It is requested to all participants, please stay online. The next session will be started soon. It will be started within few minutes.
Can I leave now?
Yeah,
Yes, sir.
you.
Yes, sir.
Thank you,
Thank you,
sir.
sir. Thank you very much.
Thank you.
Thank you
Thank
very
you
much.
very much for inviting me. Okay.
Thank you, sir.
See you later.
Dear participants, the feedback link will be given at the end of the today's program in chat box and WhatsApp group. Please fill and submit it by tonight. It is mandatory for all participants to submit feedback for the attendance purpose. Otherwise, you will be considered absent. So it is compulsory to submit your feedback by tonight. It is requested to all participants, please stay online. The next session will be started soon.
Dr. Baron is about to join.
Yes, sir.
Our next speaker is about to join within 2 or 3 minutes.
Participants, please stay online. The next session will be started soon. Dear all participants, the feedback link will be given at the end of the today's program in chat box and WhatsApp group. Please fill and submit it by tonight. It is mandatory for all participants to submit feedback for the attendance purpose, otherwise you will be considered absent. It is requested to all participants, please stay online. The next session will be started soon. And one more
Madam
thing.
Varun sir is here.
Okay, sir. So then we start. Good evening, sir. Good evening, everyone present over here. So now we will proceed for our next session. I invite Dr. Varun Sharma, Associate Professor, IIT Roorkee, to deliver his talk on evolution of micromachining and nano-finishing and overview. But before his talk, I would like to brief about Dr. Varun Sharma. Dr. Varun Sharma, currently working as Associate Professor, Department of Mechanical and Industrial Engineering, Indian Institute of Technology, Roorkee. Dr. Sharma did his BTech and MTech from Guru Nanak Dev Engineering College, PTU, Jalandhar in 2011 and 2013 respectively. Sir did his PhD from IIT Delhi in Mechanical Engineering in 2017. Sir has 12 years of teaching and research experience. He has served his service in many organizations like Lovely Professional University, Indian Institute of Technology, Delhi, Birla Institute of Technology and Science, Pilani, and now in IIT Roorkee. Dr. Sharma has guided 14 PhD, 7 MTech, and 10 plus BTech students while working at different universities during his career. He has 50 plus publications in national and international journals and 15 publications in international and national conferences to his credit. He has 5 Indian patents to his credit. Dr. Sharma has written one book on additive and subtractive manufacturing process, principles and application, and 4 chapters for different books published by international and national publishers. Now it's time to hear from our speaker, Dr. Varun Kumar Sharma. It's over to you, sir.
Thank you. Thank you for the introduction. Am I audible?
Yes, sir.
Okay, let me just share out my screen first. Yeah, is the screen visible to you?
Yes.
Yes, sir. Now it is visible.
Yeah. Good evening, everyone. Thank you for the introduction. Myself, Professor Varun Sharma. I'm working as an associate professor in Department of Mechanical and Industrial Engineering, and I'm also a joint faculty in Department of Design at IIT Roorkee. So the lab that I have over here at IIT Roorkee is dwelling into 2 different domains. One is additive manufacturing, other is subtractive manufacturing. So the lab that we have is additive and subtractive manufacturing. So whatever route we follow over here, the prime motive of that particular research is that whether we work in any sort of manufacturing, we need to provide up the sustainable solutions. So through this particular lecture, I would like to highlight how micromachining has been evolved and how nano finishing is going to provide up the solutions for certain unanswered questions and what work we have done in this particular regard, whether we have worked for abrasive flow machining, what patent we have got out of it, and how this could be used for each and everyone over here in this particular meeting. So I will try to keep it simple and try to give you the essence of this particular talk. So when we talk about manufacturing processes in particular, then those manufacturing processes are primarily categorized into 2 different domains, the additive manufacturing and the subtractive manufacturing. So in additive manufacturing, what we have is we do up the material addition in a layer by layer manner. Whereas when we talk about the subtractive manufacturing, we remove up the material in the form of chips. Now, During this course of material removal in the form of chips, it is further divided into two different categories, the conventional machining processes and the non-conventional machining processes. So in manufacturing in particular, when we have to manufacture up a product, we generally go for certain primary processes and certain secondary processes. So primary processes are primarily meant for providing up the desired shape, providing up the desired form to that particular object, whereas secondary processes are being required to provide up the desired surface finish, to provide up the desired mechanical properties that is being sought up from that particular product. So in this particular domain, when we talk about the conventional manufacturing, can I use up a pointer over here? This, just a sec. So when we talk about the conventional manufacturing processes, these conventional manufacturing processes always require up a tool in contact with the work material. Only then the material removal is there. So whether it is turning, milling, grinding, or drilling, all these particular processes always require up a contact between the tool and the work material. And we know that wherever there would be a contact, there would be friction, and wherever there would be friction, there would be wear. Now, because of this friction and wear, the desired surface finish that we get up through the conventional machining processes is not good. So they are generally used as a primary processes. Therefore, there is a need of certain non-conventional manufacturing processes, which are primarily known as the secondary manufacturing processes, whose main motive is to provide up the desired surface finish and the desired surface integrity. Now, these non-conventional machining processes are primarily divided into three different types, depending upon the source of energy that we are going to use. Now, because in these non-conventional machining processes, there is not a contact between the tool and the work material, it is kind of a tool-less manufacturing. There is no friction, there is no wear that is being involved. So the surface finish that we get over here is comparatively good as compared to the conventional manufacturing processes. Now, whether we talk about the mechanical processes, it has further categorization. There are different types of the mechanical based processes. It is ultrasonic machining, abrasive jet machining, water jet machining, and abrasive flow machining. So there is a certain kind of a mechanical action which in turn is going to provide up the desired surface finish and the surface roughness. However, there are also certain thermal-based processes, whether it is electric discharge machining, LBM, EBM, plasma arc machining, which are primarily used for removal of the material at the atomic level. There are certain electrochemical and there are certain chemical based processes also. Now, among all these particular processes, a process which can at the same time give you a good amount of material removal and at the same time give you a good amount of surface finish is one particular process is abrasive flow machining, which we call as the AFM. Now, in this particular leg, let me just next. Yeah. Why is it not moving? Yeah. So in this particular leg, when we talk about the finishing processes, they are being categorized as again a conventional based processes and the non-conventional based processes, because many a times the finishing is generally done with the help of abrasives. They are not being done with the help of a cutter or a tool. Even if they are being used, the surface finish over there can never be in the range of nanometers. So in the conventional based finishing processes, we have further two categorization of the processes. Either they may be a bonded type abrasives or there may be certain loose type abrasives. So when we talk about the bonded abrasives, whether it is grinding or honing, there is certain limitation onto the surface that you can finish. Either it will be producing up planar surfaces or a particular profile, but wherever there is a free form surface, I cannot use up a grinder or a honing machine. On the other hand, when we are talking about the conventional based processes, that is based upon loose abrasives, we are either using up a polishing or we are using up a lapping based processes in which the abrasives are still free to move in any of the direction and we can get up the desired surface finish. In the non-conventional, we have a large leg of the abrasive processes, whether it is abrasive flow machining, magnetic abrasive finishing, magnetorheological finishing, or the magnetic float polishing methods. Over here, just a sec. Yeah. So over here, one particular process which was primarily used for the deburring operation is known as an abrasive flow machining, which has a unique property that it does not have any kind of a rigid tool about which that finishing could be occurring. So in the year 1960s, when this particular technology was being invented, they was primarily used for the deburring operation, and this particular process required up a tool which was self-deformable in nature. So it was not rigid. It can freely flow. It can freely change up its particular shape. So that is why this particular process is used for providing up the finishing, which may be of the order of nanometers for additively manufactured parts, turbine blades, gears, nozzles, even in the recast layer finishing, which is there for the electric discharge machining. So as compared to the conventional limitation in terms of finishing of flat pieces, cylindrical or simple shapes, you can virtually finish any particular sort of the material because of the self-deformable characteristic of this particular abrasive media. Also, the most important thing is whenever we do up these finishing processes, whether we are doing micro or the nanoscale of the finishing processes, there is always certain degree of temperature rise. So if we do with the grinding is a process which require up the highest amount of specific cutting energy. So because of this particular temperature rise, there is a chance of the degradation of the surface integrity. Now, to get rid of it, we desire a finishing process which does not require any kind of a temperature rise. So AFM is a process in which you can do up the finishing process even with the temperature of 25 to 30 degree centigrade. So this is a conventional abrasive flow machining process. So you can see to the source, these are some of our research papers in which we have explored this particular process for the micro and the nano finishing. So what we have up over here is we have an upper cylinder and a lower cylinder. In between, there is a fixture which holds up the work material. The only challenge up over here is that depending upon the shape or the profile of this particular workpiece, you have to alter up or you have to change up the fixture. So what is there? All the abrasive media is there in the upper cylinder. With the help of this hydraulic plunger, you move up this particular abrasive throughout this particular workpiece and it gets collected into the lower media cylinder. Then you push up the media, you push up that particular abrasive laden media from the bottom to the top. So what will happen, because of this to and fro motion, the finish of this particular part could be highly improved. So this is the conventional mechanism of the material removal. So if you look to this particular mechanism, so these are certain loose abrasives. Now these abrasives can be of spherical shape, they can be of any irregular shape. So when these abrasive particles come in contact with the work material, it is being subjected to two different kinds of forces. One is the axial force, which is moving this particular abrasive in the downward direction. And one is the normal force, which is indenting this particular work material into the workpiece. Now, because of this combination of the axial force pushing it down and the normal force pushing it towards the work material, there is some amount of material that is being removed from this particular thing, and that goes into the abrasive media in the form of these debris. So what is happening because of this to and fro motion, there is always a new material, there is always a new abrasive that is coming in contact with the material, and a large amount of material removal is occurring. Now, because the indentation of this particular abrasive into the work material is relatively smaller, the finish that we get over here does not have any kind of furrows or the scratching marks. So because of that, you can achieve up the finishing even in the order of nano. So there are three different material removal mechanism. One is the rubbing action, which is because of the free flow of this particular abrasive. Other is micro plowing, which helps in flattening of these asperities, and other is micro cuttings, by virtue of which these debris come up into the abrasive media. So when we are talking about material which is ductile in nature, micro cutting and micro plowing are predominant, whereas if we want to do up the finishing of the brittle material, then only the micro cutting is responsible. Now, our motive over here is that if you look to this particular diagram is that if you want to enhance up the material removal, I have to increase up this particular normal force. Now, how to increase this particular normal force? I have to pull up this particular abrasive towards the work material. I hope my pointer is visible to you. What we have to do is we have to pull up this particular work material into the pull up this particular abrasive into the work material, as a result of which there would be more indentation and there would be more material removal rate. So how we can do that? The other thing is that if you look to these particular abrasives in this particular diagram, then only one set of the abrasive is coming in contact with the workpiece. The other abrasives, because they are moving at the central line, they're not taking part in the material removal. So could there be a mechanism by which there could be a churning action that could be initiated, and as a result of which all these inactive abrasive particles also become active? So can there be some kind of a churning that can be added to the setup, or can there be some ways by which normal force could be increased so that we can achieve up a good surface finish, and at the same time a good material removal could be there? Now, with these two things in our mind, there have been a different variants of the abrasive flow machining. It can be depending upon the flow of the abrasive media. It can be a one-way AFM in which abrasives are just flowing from up to down. It can be a two-way AFM. So what I have shown is abrasives are moving from up to down and down to up also. There is a bidirectional motion being involved. There may be an orbital or a multi-axis. Now, in order to have up a better surface finish, there have been different variants of the AFM that has been developed, whether it is magnetic field assistance, ultrasonic assistance, there may be a rotating assistance or a hybrid variants of the AFM that could be developed. The other scope that one can have while doing up the research in the nano and the micro finishing is that whatever abrasive media we are using, is there a scope of developing up a media which is free from any kind of a toxicity, which is sustainable? Once you have done up the machining processes, its disposal is also easy. Now, for that, there may be some scope of development of the media. And now with these things into mind, so these are some of the diagrams. So you see over here is the figure number A, abrasives are moving, abrasives are coming down. So what is happening? There is just one way. So in the two way, you are moving up your piston up and down. There could be multi ways in which you can have up the series of a work material connected to each other, and there can be also a zigzag motion provided to the workpiece, which result in certain kind of an orbital motion. So with these into mind, we have the different variants of the AFM that has been there. We have provided ultrasonic assistance. We call it as an ultrasonic assisted AFM. Magnetic field is being provided, which is called as a magnetic field AFM. Similarly, there could be certain rotational, or there can be combination of one with the other, which we call as the hybrid variants of this particular AFM. Now, when we talk about the media development for the abrasive flow machining, it plays a significant role in getting up the desired micro or a nano finishing, because it is that particular media which is going to hold up the abrasives against each other. So if the abrasives would be rigid enough, what will happen? You will not have a free form motion. So if the media is loose enough, the abrasives may be in a position that it does not cause any kind of a micro cutting and all. So to get all these things, we have to develop up a media which is not only sustainable, at the same time, it is also going to hold up the abrasives in such a manner that the desired surface finish could be achieved. So there have been different variants of this particular abrasives, ranging from hydrogel to silicone to rubber to natural rubbers and even to that of an MRP media. So this is the classical fishbone diagram which we made on our own, that how this particular AFM process is going to affect up the process responses. So there could be certain machine-based parameters which you can control, for example, extrusion pressure, number of cycles, media flow rate, volume of media. There could be certain media specific parameters in terms of its viscosity, in terms of the concentration of the abrasives, in terms of the type, size of the abrasives, and in terms of the temperature at which you are going to do up the machining. There may be certain variant based parameters. For example, whether you are providing ultrasonic vibrations, whether you are providing certain kind of a magnetic field, there could be an n number of secondary parameters to govern that. Similarly, there could be certain workpiece based parameters. For example, whether I want to do the finishing of a ductile material or a brittle material, whether I want to do up the finishing of the outer surfaces or the inner surfaces, what is the initial surface roughness finish. So taking all these things into loop, there could be an n number of parameters which are going to affect up your process responses. Now, what is this process response? Material removal rate and the surface finish that you can get up. Now, these are some of the applications of the AFM. You can see up for the additively manufactured part also, this is being used. So this is the additively manufactured part before finishing, and after you have done the AFM, you can see all these valleys or the pits have been removed. This is the classical example of a biomedical implant. This is a knee implant. So knee implants finishing is generally done using AFM. So this is an as printed biomedical implant. And after you have done up the AFM, you can see up the kind of a shiny surfaces that you can get. Even in the case of finishing of turbine blades, this is right now the only solution. So in case of a turbine finishing, AFM is being used. So this is the before finishing example, and this is the finishing of the turbine blades after it. So whether it is in the wire arc additive manufacturing, whether it is wire EDM'd surfaces, or even for the finishing of the gear surfaces, because the gear have a very unique profile, a profile which is free form in nature. None of a conventional finishing process could be used. So over there, AFM could be an alternative solution to provide up the desired finishing surfaces. So there is a large amount of opportunities that can be considered in this particular processes, that as of now, most of the attempts have been to develop up to do the finishing of a singular part. At the same time, all these medias that have been developed, they also have a limitation. They are rubber-based media, which are toxic, which are not at all sustainable, and they do not perform well when there is a slight increase in the temperature, because the rubbery stage of that particular media occurs. At the same time, there has been very few attempts that have been dealt up in developing new variants of the abrasive flow machining. So with that thing into mind, and some more in terms of hybridization of the processes, in terms of finishing of high-end materials like inconel shape memory alloys, glasses, and also a media by which you can get removed up the used blunt abrasives. So could there be an answer for that? Yes, for that we tried to categorize this particular thing as a packet, in which first of all we tried to develop up a media which can provide you the answers for finishing of micro or for a nano scale. At the same time, we characterized that particular media and compared it with the traditional processes to get up the desired finishing. So over here, we get up a patent on this particular media. So that is our patent, and we try to compare it with the conventional problem. So if you have up the conventional abrasive media, which is used for the finishing of turbine blades and even for the knee implants, the problem over there is to develop up this particular media, it required certain kind of a costlier equipment, which is difficult to handle. At the same time, it has certain toxic fumes, which is health as well as environmental issues. So could there be a solution to that? For that, we try to develop up a hydrogen-based media, which does not require any kind of a heater. No fumes were being released, and in very less time and in a low cost, you can develop up that media whose performance is satisfactory as compared to that of a conventional abrasive media. So what we did over here is we used up the local food grade materials and a naturally occurring materials. We used up a xanthum gum. It's a kind of a gum. In Hindi, we call it as a goond. So we had a xanthum gum. We fixed it with another biodegradable, biocompatible cross-linker, that is a locust beam gum. Added certain fumed silica to maintain the desired viscosity, and added silicon carbide abrasive particles over here. So what was the method of preparation for us is we just used xanthum gum, mixed it with LPG and keep on stirring it till you get up the desired thickness, and then we put up the abrasives into the medium. So when we were doing up, so you can see up, this is the conventional images of the SEM images of the abrasive media. These are the SEM images of the abrasive leaden media. So these irregular shapes that you can see up over here, these are actually the abrasive particles holding that particular gum. So we tried to have a different sets of the abrasive media with the motive to have a good surface finish. So when we did is we tried to have up its viscosity testing. Now what is happening once your media is moving up and down, it is being subjected to a particular strain rate. Now, when it is being subjected to a particular strain rate, there may be some kind of loosening of that particular media. So what we did over there is we try to analyze its shear modulus as well as a loss modulus and try to find up a point about which there is a shear thinning occurring. So if you look to this particular diagram, so what you can see up is that all of these different sets of the abrasive media are actually having up a shear thinning character. So with time, it is going to thin. What I mean to say is that with time, the holding capacity of that particular media for the abrasive is going to decrease. It is going to shrunk down. So it may be good for a certain range, but it may not be good for the another range of the set of parameters. So this is the viscosity profile with the shear rate. So when we did is, now if you see is, this is yellow colored line is the viscosity variation with the shear rate for the conventional media, that is a rubber based media. Now this is a viscosity profile for the existing literature in which the viscosity is gradually decreasing, means a shear thinning is occurring, and after some time it is becoming more and more thick, which may not be desired because your abrasives will be held up and it will not be able to have a free form movement, as a result of which the finishing would not be good. Now, as compared to the literature and as compared to the thing in the practice of most of the AFM machines, what we did is we developed up this gray colored media, which whose thickness was very good. At the same time, it was just showing up the shear thinning characteristics, which is perfectly right for the abrasive flow machining processes. Now, from this TGA diagram, you can see up that around 74 degrees centigrades, there is a weight reduction of the media. Now, how much weight reduction? From 100% to 76%. So it means what does this signify is that once you reach up a temperature to 74 degrees centigrade, there may be certain weight losses. Now, what I mean to say by weight losses, the abrasives holding power would reduce. But ideally, in AFM, the temperature is going to be there of the order of 30 to 40 degrees centigrade, whose weight loss is not that significant. So it says that this particular media that we have developed is good enough, and it could be used for the abrasive flow finishing processes, though it is being made up of the biocompatible and the biodegradable media. Now, from the FTIR analysis, what we found up is that whatever we have used as the media, as a cross-linker, or as the thickening agent, whether it is a fumed silica, locust bean gum, or the xanthum gum, they have actually bonded against each other. There has been different bonds which have been categorized from this FTIR peaks, and it means that it is not, the different ingredients are not loose enough, rather they have mixed up properly in this particular medium. Now, when we tried to compare up this particular process from the conventionally used hydrogel polymer based media. So you can see up that the material removal rate is increased as compared to this green colored line. The orange colored line is higher. At the same time, the percentage improvement in the surface finish is also not that good, but it is comparable. So it is 15, it is 13, it is 31, it is 24 in nature. So no doubt the performance wise, I am able to get up a higher material removal rate. It is also at the point of the cost wise that these hydrogel based media are good enough. For example, if I compare up making up 1 kg of that particular media, our approach is going to have just 180 rupees per kg, whereas the conventional polymer based abrasive media, which even some of the research labs are using, they're costing around 370 rupees a kg. So from the economics point of view also, this particular process could be used over here. You can see up the surface finish. So this is the unfinished part. The surface finish is of the order of in the micron ranges, but what you can see is that after you have done up the finishing, all these particular peaks have flattened up, and you are going to have up a surface finish which is of the order of 0.8 to 1 microns. So that is the beauty of this particular media, that it can do up the removal of the material asperities even at a relatively faster pace. At the same time, the other problem with the conventionally used abrasive media to even get the desired surface finishes, that how you are going to dispose of the material. Now, what I mean to say is that let us say that you have done up 100 runs or 200 runs, and after that there have been certain debris which have come up into the abrasive media. So could there be some means by which those debris can be taken out? As of now, there is no answer to it, because you have to throw off that particular polymer based media directly into the nature. So there is no answer to it. But through our particular media, what you have is you are going to just give 10 washes. Now, what is happening? First wash, fourth wash, there is certain kind of a turbidity. Seventh wash, the turbidity has gone. So what is happening after 10th wash, you can easily separate up the abrasives because it is a hydrogel based media. So all of the hydrogel is being taken out and they are being lighter in nature. They will be at the topmost of this particular flask, and all the abrasives become, because they are heavier in nature, they will be settling down onto this particular flask. So as a result of which, what is happening is that you can easily separate out the abrasives from the conventionally used abrasive media, which is not there in the conventional media. Now, because of these beauties, This particular abrasive media has been patented at the Indian Patent Office. And with these things into account, we tried to see that no doubt we can get up the finishing, which is of the order of microns. Can we have up the finishing of the order of nanometers? Yes, for that, we tried to develop up a new variant of the AFM. So I started up my lecture saying that when we want to finish up the abrasive, we want to use the abrasive flow finishing processes. So over here, there is a scope of the variant development. Now, what I mean to say, there is a scope of the variant development. You can use, by some means, you can make up the inactive abrasives active. By some means, you can increase up the normal force or the indenting force. So what we did is we tried to amalgamate two different things. One is an ultrasonic vibrations and other is the magnetic assistance. So what we did over here is, if you can see to this particular diagram, this is the workpiece, the cylindrical shaft that you can see. This is the workpiece that is in contact with the ultrasonic horn. Fine. At the same time, at the periphery of this particular horn, there are a large amount of electromagnets. There are 4 electromagnets that are being surrounded. Now, what are these electromagnets going to do is they're going to churn up the abrasive media within this particular location. So what will be happening? There would be certain kind of a churning. At the same time, because of this ultrasonic motion, there would be certain kind of what you say uh, striking of the abrasives against the work material. So by virtue of it, we tried to analyze up the material removal rate and analyze up the surface finish. So this all setup, we again got it 3D printed. So this is the setup that we developed for the process. So this is our fixture. Here lies up the workpiece. This is our upper cylinder, bottom cylinder, and between this upper and a bottom cylinder, we can have up the movement of the abrasive medium. Now, what we did over here is we tried to use up a work material which is a 3D printed part. Now, when I say up a 3D printing, it is primarily a tool-less manufacturing whose motive is that it gives you a very good surface finish. But the problem with the additive manufacturing, as we are doing research in the additive manufacturing domain also, but the problem with the additive manufacturing is there is always an inherent defect, which is called as a staircase defect. Now, what is this staircase effect? The surface finish is not good. Now, because the surface finish is not good, it always requires certain kind of a secondary processes, and only after that it could be used for the 3D printing applications. So what we did is we used ABS and PLA as a work material and tried to analyze its material removal rate and the percentage improvement in the surface finish for 3 different sets of parameters. Now, mind it, we are working with ABS as well as a PLA. One is a relatively harder material and other one is a relatively softer material. So from a hard to a soft, how the same machining parameters, how the same machine could affect, that was the thing under consideration. So the upper half is going to give you the demonstration for the variation in the parameters for ABS, which is relatively hard, and the bottom half is showing you the graphs for the work material, which is relatively small. So what you can see up over here is for a softer material, the material removal rate is more because the curve is this is particular steep. Now, as a result of which the material removal rate is much more in case of a PLA, because ABS is relatively hard. Over here, the material removal rate is relatively less. Now, what we mean by abrasive concentration, the amount of abrasives that are there in the abrasive media. Now, if there is more amount of abrasives, there should be more amount of material removal rate. Ideally, it is not so. So what you see is that the material removal rate is increasing till 50%, but after you increase it from 50 to 60%, the material removal rate is not increasing that much. Now, the reason for that is that there may be certain kind of collisions within that particular abrasives, as a result of which the material removal rate would be less. So it is not so only 100% loaded abrasive media will give you the desired surface finish. You can have up the loading of the abrasive media even less than that of the 50%. So on a similar line, we try to analyze up the surface finish for the ABS and for the PLA. So that is what you can see up over here is that the amount of percentage improvement in the surface finish, it differs from media to media, it differs from medium to medium, and it differs from the material to material. So based upon this particular analysis, we try to optimize up the parameters for getting up the desired surface finish for a 3D printed surfaces. So over here, what you can see is that for an unfinished part, for a layer thickness of 0.1, see all these line marks which you can see up for a 1 micron layer thickness, they are being taken out, whether you are working for ABS or you are working for PLA. So similarly for 0.2 and 0.3 type of a layer thicknesses, the surface finishing is significantly improved. Now, because this particular process could be used for additively manufactured part, it could be used for even the conventionally built parts through castings and all. So the next motive was that could there be some solutions by which we can remove up the deep scratches. Now, these deep scratches are responsible for getting up a poor surface finish at the nano level. So at the micron level, the surface may appear to be good, but at a nano level, these deep scratches are ineffectively to be removed. It has a very low finishing performance for the modern set of materials. So it may finish very nicely copper, brass, but it may not be able to finish titanium, nickel for those super alloys. All at the same time, there is a scope of large amount of finishing time. So even for your turbine blade finishing, for your knee implant finishing, it takes hours to get up the desired surface finish. So could there be some mechanism by which we can improve of the finishing performance? Could there be a mechanism by which we can have a better interaction of the abrasive with the finishing? For that, we provided two different kinds of assistance, the ultrasonic assistance as well as the magnetic field assistance. Now, this is the ultrasonic horn that we designed a two-stepped ultrasonic horn made up of material SS316. We tried to develop our own course. We tried to develop our own electromagnets and try to see that how magnetic field intensity is varying, so we could achieve up a magnetic field of the order of 0.5 to 1 Tesla. So this is the schematic of that particular setup. So if you can see up over here is these are the abrasive particles which are there, and these abrasive particles are being given up a churning motion because of these particular set of the electromagnets. This was being again patented in the Indian Patent Office to get up the desired nano finishing. So this is the actual setup that we printed. We developed this particular setup from scratch. Everything has been made in-house, from these hydraulic plungers to all these electronic circuitry. So it had a large amount of units, from magnetic field assembly to voltage stabilizer to a PLC based RPM controller. So at what RPM you are going to, at what rate you are going to move up the abrasive from up and down, everything could be controlled using this particular setup. Now what we did is we tried to finish up a material which is biocompatible in nature so that its usage can be even in the medical domain. So what we did is we used a pure titanium. That's a grade 2 material, which is biocompatible, and it is being used in a large amount of implants and all. And with our media and different versions of the additively manufactured part, different variants of the AFM, this is a conventional and the most big breakthrough that we can achieve through our research. For a conventional AFM, if there is 9 mg of a material removal, we can have up to 22 mg of a material removal within the same time. So it means we can improve of the material removal by 144%. At the same time, if there is a percentage improvement in RA from 18%, we can achieve up 51% of the improvement, which means around 177.27% more amount of material removal as compared to a conventional AFM. So these are the different variants, that is magnetic assisted flow finishing, rotary magnetic, ultrasonic assisted, and this is where our particular machine and our particular patent lies, which can give you very high dividend in terms of material removal as well as in the surface finish. We tried to analyze this particular process. We did certain statistical modeling to make sure that the desired surface finish is being achieved. And over here, we took 5 different sets of parameters: magnetic flux density, rotational speed, vibration of intensity is the ultrasonic vibration, extrusion pressure, and the iron powder concentration. Now you will worry that I'm using silicon carbide as an abrasive, but I have to add iron. Now the reason why I'm adding iron is because, just a sec, because it will be only this iron. Silicon carbide will not be attracted towards the magnetic poles. It will be the iron that will be attracted towards the magnetic poles, as a result of which there would be a churning action. So your abrasives are being held up by certain iron particles, and those iron particles in turns do up the finishing. So with that thing into mind, these are some of the regression models that we developed for the material removal and for the percentage improvement minded. These regression models are valid only for this particular range of the process parameters. So these are some of the conventional graphs that we did for the magnetic flux density variation with the material removal rate, RPM, intensity, extrusion pressure, and a percentage concentration. I would like to discuss this with you. That is how this nano finishing could be achieved, or the micro finishing could be achieved by the variation of the magnetic flux density. So what is the case is, we varied up the magnetic flux density from 0.06 Tesla to 0.3 Tesla. So as I'm increasing up the magnetic flux density, so what you can see is that the percentage improvement in RA is occurring. Now, if there would be large amount of magnetic flux density, what will happen? The abrasives will be pulled more towards the workpiece, as a result of which there would be a higher indentation force, and a higher indentation force in turn will result in a good surface finish. So that is what is being shown up over here. As you are moving higher and higher in the magnetic flux density, you are going to get up a better surface finish. At the same time, if I am increasing up the intensity of the vibration, now what I mean to say by the intensity of the vibration, the amplitude of the vibration. So if I'm working at 100% intensity, it means there is more vibration being provided to the abrasive particle. More would be the abrasive particles vibration, there would be more indentation to the workpiece, as a result of which there would be a better surface finish. So similarly is the case with the other parameters also. So we can have up the customization. So what we have to do is, for a particular set of material, you are going to get up these A, B, C, D, and E, which are the process parameters, and you can compute up that what is going to be my percentage RA. Mind that if your object is having up a very poor surface roughness, I mean to say a poor surface finish, there would be a more scope of getting up a higher material removal rate, because it is already having a large amount of peaks for a particular size of the abrasive. So if I'm already having up a surface which is of nanometer range, and I want to further reduce it, the surface finish further down, for that I have to reduce the size of the abrasive, because that is in turn is going to govern up the material removal. So these are some of the interaction effects of the parameters on the material removal rate. So you can see up over here is the initial unmachined surface is having up a surface finish of 82 microns, whereas the desired surface finish for the machined specimen is of the order of 20 microns. So we compared up the statistical model, and the statistical model was very good. It had a percentage error of less than that of 5%, which is considered a conventionally good model for predicting up the output responses in terms of material removal rate and the percentage improvement in the RO. With that thing into mind, we try to say that what is the science behind this particular thing. So through this journey, what we did is we tried to develop up the abrasive flow media. We tried to have our own set of the abrasive media. We tried to have our own variant of the abrasive flow processes. We tried to finish from a range of the work material, that is from polymers, that is from ABS, PLA, to metals, that is titanium, which is hard to cut. But what all is governing, what all is happening when I'm doing up this particular material removal rate? So for that, what you can see up over here is we tried to analyze up how this particular mathematical modeling can govern up the desired surface finish. So for that, we did up a very extensive study. We started with certain basic mathematical model assumption. So what we assume is that ideally the abrasive and the iron particles are spherical in shape. Fine. Now, this is also a problem. The problem is that if I will be using up iron and the abrasive particles, which will be spherical in shape, the material removal rate would not be good. So if you look to this particular diagram, I hope I'm able to draw it. Just a sec. Yes. Yes. Let us say that I have an abrasive particle, which is an irregular shaped abrasive particle. And at the same time, I have an abrasive particle, which is spherical in shape. Now, what will be the case is, now there is an n number of cutting edges available. So if I look to this particular abrasive, this is also a cutting edge that can be doing up the finishing. This also is a cutting edge. This also is a cutting edge. This also is a cutting edge. So there could be an n number of cutting edges if the abrasive particle is irregular in shape. Am I right? Now, if you look to this abrasive particle can just rotate about this particular axis, but there is no sharp corners which is available. So if I want to remove up the material from this particular periphery, so there could be an n number of cutting edges which can be responsible for creating up an indentation into the work material. So ideally, if we want to have up a better surface finish, the abrasive particle should be irregular in shape so that n number of edges could take part in the material removal. But just for the mathematical ease, we assumed up that the abrasive particles are spherical in shape, uniform in size. But if we go up into the market and purchase up the abrasive particle, this is how the abrasive particle actually flow. They have a normal distribution. Fine. Most of the particles will be of central median, but they may be of extreme right, or they may be on the extreme left. So there may be a large scope of the variation in those particular abrasive particles. But for our ease, we assumed it to be uniform in size and homogeneously distributed. Also, we assumed up that there is no kind of chip removal from the abrasive. So after some time, once you are doing up the machining, there is a good number of chances that these sharp corners also wither away. They also go away with the time. But what we do is we generally do not consider it for the mathematical modeling, just for the ease of the mathematical purpose. Also, we assumed up that if this is your work material, it is not flat in shape, rather it is having certain irregularities which are triangular in shape. Now, so if I have a work material and I want to finish it, I have to get rid of all these triangular asperities. Fine. So the peaks are assumed to be triangular in shape and uniformly present onto the work surface. Now, just a sec. Let me just go through it. Yeah. So, yeah. So in case of a conventional abrasive flow machining in which there is a linear motion, that is being provided to the abrasive media. Now, because of this magnetic assistance, so what is happening is there is a certain kind of a churning action that is being produced, as a result of which the abrasive particles will not follow up a linear line, rather they will be following up a path which will be helical in shape. Is it so? So we try to define up that how these abrasive particles are actually moving. So we defined up its mathematical position, did up its derivative to find up the velocity, and then try to find up that what will be the resultant velocity of that particular abrasive particle. Now, with that thing into mind, just a sec. Yeah, with that thing into mind, we tried to find up that how the velocity is varying with the time. So we did up a MATLAB coding and we found out that the abrasive velocity is fluctuating from 1230 mm per second to 1140 mm per second, which is quite a good amount of velocity to get up the desired surface finish. So we took this particular thing, which we have computed from this particular mathematical relation, for a certain set of the parameters, this as an input for our mathematical model. Now, this is the conventional velocity which is there for the, just a sec. Yeah, this is the conventional velocity which this particular abrasive particle is being subjected to. So what is happening? There is axial velocity VA, there is a tangential velocity VV. At the same time, there is also a vibrational velocity which is accounted because of the ultrasonic assistance. Now, we computed it. We computed the axial velocity because of the applied pressure. We computed the tangential velocity because of the rotation. We computed the vibrational velocity by virtue of the frequency of vibration and the amplitude of vibration, and tried to compute up the resultant velocity. Now, but this resultant velocity is different from the process that we have developed. So what is happening over here? As compared to the axial force and the tangential force, which is common in a conventional AFM also, we found up that there is a normal force, which is because of the the electromagnets which is beneath this particular tool. There is a magnetic force, there is a centrifugal force, at the same time there is a vibrational force also. So if you look to this particular diagram, there is only one set of the arrow which is plunging this particular abrasive into the work material, whereas over here there are different sets of arrows. So the indentation force is a sum of Fn, Fm, Fc and Fv, as a result of which the indentation force is increasing. Now, because this indentation force is increasing, you can have up the micro or the nano finishing for the same set of parameters for this particular process. We try to compute up the normal force, axial force, and then try to compute up the magnetic force, which is in turn dependent upon the magnetic flux density. We did up all these particular sets of calculation. So if you look towards the resultant force in our particular set, it is far more than the resultant force which is there in the conventional AFM process. So this is the variation of the magnetic flux density. So a magnetic flux density is higher at the periphery, but as you move towards the center, the magnetic flux density is decreasing. Now, because of it, you get up a very good surface finish, which is close to the proximity of that particular electromagnet, whereas onto the extreme, the surface finish is not at all good. Now, how these abrasive particles are being held up? So for that, we tried to analyze the thing and we assumed up that these abrasive particles are forming up a BCC sort of a geometry. So this golden color portion that you can see are the actual iron particles which are holding up the abrasive particle. So the moment I increase up the magnetic flux density at this particular juncture, what will happen? All of these iron particles will start moving towards the periphery. And as they start moving towards the periphery, what will happen? These abrasive particles will also get in contact and they will also start moving towards the periphery. And as a result of which, the material removal rate would be high. So we analyze that the material removal rate for the desired surface finish, it follows two different kinds of criteria. So one is that it follows a steady state and at the same time it follows up a transient phenomena. Now, what we mean by a steady state, we mean to say that the process remains constant throughout the process. Material finishing per finishing cycle remains constant throughout the process. And it also depends upon velocity, length of contact, resulting forces, number of active abrasive, and the work material hardness. Whereas the transient material removal per finishing cycle, it is dependent upon the irregularities which are occurring onto the workpiece. So when we talk about the surface finish, it is a combination of the steady state as well as it's a combination of the transient phenomena. So we tried to analyze up the material removal. So we found up that this is the abrasive particle, which is spherical in shape. And this spherical abrasive particle is being subjected to indentation force, which we have just discussed. It is the sum of the axial force, vibrational forces, and all. So what will happen? This abrasive particle will indent the abrasive into the work material, and what will happen, this orange colored portion that you can see here is the actual amount of material removal. So if there would be a more indentation, it will more penetrate. If there would be more indentation, it will more penetrate. Fine. So what will be the case is over here 2b, that is the diameter of this particular crater, is less than that of the diameter of the abrasive particle. Fine. Now, if it is equal or more than that of the diameter of the abrasive particle, what will happen? This abrasive will become a unity with the workpiece. It will not be able to further remove because it has entrapped into that particular workpiece to a very larger extent. So you have to make sure that this indentation 2b is less than that of a dA, and whatever is this particular indenting force, that indenting force is going to remove up the work material, which is being shown up by this particular line. So we tried to analyze it for the steady state as well as for the transient state, and we tried to have up the material removal. Now see, these are the height of the peaks. These are the peaks which are being arranged around the periphery of that particular workpiece, and these surface irregularities are there. Now, abrasive particle is coming. Once the abrasive particle will move from up and down, what will happen? It will gradually flatten up these particular triangular peaks. When it is moving from down to up, it will again gradually flatten up these irregular peaks. As a result of which, there would be a to and fro motion and the chip removal would be there. Now, with that, we combined up the steady state with the transient phenomena, and we landed up to this particular equation by which you can just put up the input parameters in terms of what is the hardness of the work material, what is the initial roughness, what's the diameter of the abrasive particle, what is the indentation that you are having, by what velocity you are moving your abrasive up and down, by what velocity you are moving your piston. Now, once you give up all these desired parameters, this particular process can compute whether you are going to work for the micrometer range of the material removal, or you are going to work for the nanometer range of the material removal. Now, with that, we tried to categorize out the material removal and the surface finish, and we try to compare up the surface finish in terms of number of cycles. Now, if you look to this particular mathematical relation, which is very interesting, once you need to switch from micro to a nano finishing, you can see up this surface finish is directly dependent upon the number of cycles. So if there would be a large number of cycles, there would be a more amount of material removal rate. If there would be a more amount of material removal rate, better would be the surface finish. Now, with that, we did certain categorization and we did up the experimentation for around 160 cycles. Now, the moment I did it for 160 cycles, what we did is we were able to just remove 2 mg of a material removal, which is very less. You will say that it is hardly any kind of a material removal, because material removal is dependent upon the diameter of that particular abrasive. So if I have the same diameter of the abrasive particle and I'm doing it UAMAFM for 160 or even for a 1600 cycles, those abrasive particles may become inactive. So you have to select up the abrasive particles for the desired amount of the surface finish that you are going to have. I will not discuss it over here, but what you can see, up over here is that the percentage error for this particular mathematical model is 7%, whereas our roughness is going to give you a prediction of with an error of just less than 2.5%. So this is how the material removal rate varies with the parameters. So what you can see over here is that as I am increasing up the amplitude of vibration, fine. The moment you increase the amplitude of vibration, what you are doing is you are striking the abrasives more and more towards the workpiece. More and more would be the striking, more would be the material removal rate. That is what is being depicted with this particular graph. Mind it, all other particular parameters are steady and they are being noted down over here. Now, similarly is the case with the frequency of vibration. More would be the frequency, more would be the axial force, more would be the axial force, more would be the indentation, and as a result of which the material removal rate would also become higher and higher. Is it so? Now, similarly, is this the case with the magnetic flux density? Now, as you increase your magnetic flux density from 0.1 to 0.5, more would be the indentation of those abrasives against the workpiece. As a result of which, more would be the indentation, more would be the plunging, and material removal rate would also become higher. However, if I increase up the RPM, number of times the abrasive moves up and downs, what you found up that there is a linear motion. So if I'm having 150 RPM, material removal rate is linearly increasing as compared to 30 RPM, but it may not increase again that steep, but it may become a plateau kind of a thing, because after some times the abrasive particles will not have sufficient time that it can abrade against the work material. At the same time, initial roughness is also going to play a predominant role, because for a particular set of parameters, material removal rate again linearly follows the same trend. Now, similarly is a case for the amplitude of vibration. Now, as the amplitude of vibration is increasing, what is happening? The moment I increase up the amplitude of vibration, there is more striking, there is better surface finish. So that is what is being shown up over here also, that you can get up a surface finish which is of the order of 0.75 microns as compared to 0.95 at 2 amplitude of vibration. However, the frequency is not following up a steep decrease, but it is fluctuating. So it is decreasing, then becoming more and more constant. Now, the thing over here is when the abrasive particle is doing up the micro or the nano finishing operation, what is going to happen is that you are going to provide the sufficient time for that particular abrasive to take part in the material removal rate. Now, if it is not going to take part in the material removal rate, then it is insufficient. So that is what is being shown up over here, that a higher frequency may not be a good option. It is not just following a decrease. After some time, it may increase also. Similarly is the case with the magnetic flux density. Higher is the magnetic flux density, higher would be the force by which the abrasive particles would be striking against the work material, and as a result of which the surface finish gradually decreases. Similarly is the case with the number of RPM and the initial surface finish. Now, before I conclude up the session, I would like to take you to this particular diagram that I started with the initial part, so that I can culminate up at the conclusions with that particular slide only. So from this particular analysis, what we can, where is it? What we can think of is that material removal is an analogous to that of a surface finish. Higher would be the material removal, better would be the surface finish, lesser would be the material removal, poor would be the surface finish. Now, with these two contradictory things into our mind, so the only solution by which this AFM could be used for the finishing of these turbine blades, these biomedical implants, these EDM parts is that there has to be some kind of an optimization. There has to be some kind of multi-objective optimization to get the desired surface finish at the same time with a good surface material removal rate. So if you see to this particular thing, for the to get these kind of shiny surfaces, to get these kind of highly from the matte to glossy kind of a finish, you have to not only optimize your process parameters, but at the same time, you have to selectively choose the type of the abrasive, the size of the abrasive, and at the same time, the concentration of that particular abrasive into the abrasive media. So these sharp edges, which are there for a Pelton wheel or the turbine blades, they may be used, they may have certain kind of a burrs. So all these deburring, all these micro level of the material removal is being possible only and only by this AFM process. There is no other alternative as of now, even in the existing industry, to do up the finishing of those small holes which are there in the turbine blade. So even the DRDO's labs, they are being using AFM for that particular application. Now, with that, I would like to conclude up my lectures with the conclusion part. So from all these variants and through the 3 patents that we got up in this micro nano finishing process, the conclusion can be drawn in like that. So the first conclusion that we can have up for this particular process is that we have been able to develop a low cost abrasive media. So which is sustainable in nature, which is cost effective, as well as, and beyond that, it has a very good surface finishing characteristics as compared to that of a conventional abrasive media. Point number 2, we have been able to finish even the additively manufactured part whether it is plastic, ABS or PLA, we have been able to do up the finishing even for the super alloys that are titanium grade. And as compared to a conventional AFM in the market, we are able to increase up the material removal rate, increase up the material removal rate by 144% and the percentage improvement in surface finish by the 177%. So at the same time, our research group is the first, I would rather say, in the world which has developed up that how this micro nano finishing could be achieved by the developing certain mathematical models. So that is also a new research contribution that we have developed. So we developed up the statistical models, we developed up the mathematical models, we developed up a hydrogel based media which do not require any kind of a heater to produce, to manufacture it. It is just by the stirring action. No hazardous fume, no toxic fumes would be released up. And this at the same time, because of the amalgamation of the external ultrasonic and the magnetic assistance, this combination is going to give up a large amount of dividends. So these are the 3 patents that we got up through this publication, through this project. And these are some of the international journals and the conferences that we published for the paper. So that's all from my side. I have deliberately kept up the last 5-10 minutes for the doubt session if we can have up a one-to-one interaction with the participants. Thank you.
Yes, thank you, sir. Participants, if you have any question, please raise your hand. If anybody wants to ask question, please raise your hand.
There is something in the chat box.
Hello, good evening, sir.
Yeah, please, good evening.
This is RP Singh from IPS College,
Yes, please.
Associate Professor from Mechanical Department.
Yes, sir.
Sir, as you discussed, in this micro manufacturing process, generally MRR rate used to be very low.
Yes.
Okay. And we use this MRR where feasibility is there, like in turbine blade. Okay. And actually, we worked in Gajra Gear Private Limited, where lapping process was doing on a gear. That is also finishing process, lapping process. Okay. So what I just want to know, where we do some sort of DOE analysis and Taguchi analysis, where we use combination of factors to see the effect on the surface finish. You just explain कि MRR depend on particular dependent variable, but can't we have a combination of variables where we can do a detailed study? Means suppose we can control 2 or 3 parameters simultaneously, and we could gauge the see the result on that MRR rate. Because sir, individually you shown very good graph, and it's really eye-opening. Means each factor, how the MRR rate is being affected. It was depicted very well, sir. But can't we have a combinations of the parameters?
Yes, you can have a combination of the parameters. If I can just show you the slide again. Just a sec. So these were the individual graphs. At the same time, these are the surface plots.
Okay.
These are the surface plots. Now you see how the combination of magnetic flux density and the percentage intensity is varying the material removal rate. So you can have up the combination of the different parameters to control of the material removal rate, so that you can have it.
Yeah. Yes,
These
more than 2 dimensional. Yes.
This is what we call as a 2D graph. So if I'm having up a RPM of 45 and a magnetic flux density of 0.12, so from this graph you can compute up what is going to be the material removal rate. So you can have up that combination.
Okay, sir. Okay, sir. Thank you, sir. Thank you.
Thank you.
So there is Mr. Dinesh Babu who raised hand.
Yeah, please.
Sushil sir, please unmute Mr. Dinesh Babu.
Yeah,
Sir, I have a clarification.
the chat. Yeah, Rajesh,
Yes,
I
sir.
can pick it up. So
AFM will be can be used for doing polymer-based materials, which has been printed through fusion deposit modeling 3D printer. In
yes.
that 3D printed samples, can we use AFM for knowing the layers or surface of the material that we have printed?
Yes. Thank you for the question, Professor Babu. So if you look to this particular, if you have heard about my presentation, so what we did is when we talk about additive manufacturing has a one drawback that it does not give a good surface finish. So whether you are working with metals or you are working with the polymers, okay, there is something called as a staircase effect. So what we have done is we have proven that this particular technology of abrasive flow finishing could be used for the finishing of a fused deposition modeling. I give you a live example out of it. So in this COVID and all, people started building ventilators. And once they were building up ventilators, they used a large amount of a 3D printing parts to make up those particular ventilators. Now, if the surface would be rough, fine. If the surface is rough of that particular 3D printed part, what will happen? Because it is being used, you are going to blow up in ventilator, you are going to blow up the oxygen to and fro and all. So if there is some kind of a germ, that germ will strike onto, that germ will get attached onto the periphery of that particular rough surface. So during the case of a COVID, people started building these ventilators in which they used up a tri-junction. So there is one pipe and then two pipes are coming. Fine. For that kind of a connection, they use up a 3D printed parts. Now, for over there, IIT Roorkee also manufactured one ventilator during COVID. So what we said is that this critical part cannot have a very poor surface roughness. It has to be very, very good. It has to have a very good surface finish. Only then it could be used for biomedical implant. So we proved up that AFM could be used as a secondary process to finish up the 3D printed part. So that is what we have used, and it has been demonstrated in a live product also. I hope I have answered, Babuji.
Okay. Thank you, sir.
Thank you. Before I wrap up, there is always good to have a one-to-one interaction, but it could not be there. This is our website. These are the different domains on which we primarily work. These are some of the students. This is our domain. So we work in conventional machining, we work in non-conventional, additive for the biomedical application, ultrasonic assisted machining, and sustainable machining. These are some of the facilities that we have developed with time over here at IIT Roorkee. So whether you work for the polymer-based additive manufacturing, metallic-based additive manufacturing, or you are working for machining from turning milling to AFM to EDM and all. So our main thrust is into the additive manufacturing domain, which we are doing it. These all are subsidiaries of that particular thing. So if you have any particular doubt, feel free to ask me, or you can drop me a mail. It was nice discussing with you all, guys. Thank you for having me up over here. Thank you, Professor Vineet, for the invitation. Okay, there is one more question.
Yes,
Okay.
there is a question.
What is the maximum surface roughness which we can get through FDM? We generally get it up in microns. It will be generally more than that of one microns, because the maximum layer thickness that you can get up in FDM is 1 micron. So it will be more than that of 1.2, 1.3. For 3 microns of a layer thickness, it may be more than 3 also. Thank you. Ma'am, you are not audible.
Thank you. Thank you, sir, for your detailed information on evolution of micro machining and nano finishing and overview. Now, I invite Organizing Secretary, Mr. Vineet Raj Singh Kushwaha, to propose vote of thanks. Sir.
A warm good evening, everyone. I, Vineet Raj Singh Kushwaha, on behalf of the Organizing Committee of the 6 Days Faculty Development Program on Recent Advances and Applications of Manufacturing in Industry 4.0, extend my most sincere thanks to the eminent speaker, Dr. Varun Sharma, Associate Professor, IIT Roorkee, for sharing his deep knowledge on evolution of micro machining and nano finishing with us. The way he explained the topic was extraordinary. He focused on the process of machining, working, and development of AFM and its application in the real world. It will really make an impact on our knowledge and career growth. A big thank goes to the participant also for making the program interactive and enthusiastic. Thank you all once again.
Thank you, sir. Thank you, Varun Sharma, sir.
Thank you.
Thank you, sir.
Thank you. So I will believe you. Thank you. Thank you.
Dear
Very nice
participants,
lecture, sir.
Thank you. Thank you.
Dear participants, the feedback link is given in WhatsApp group and chat box. I request you all please fill and submit it by tonight. It is mandatory for all participants to submit feedback for the attendance purpose, otherwise you will be considered absent. The third session will be started at 6 p.m. on tomorrow. I request you all please be present 10 minutes prior. Thank you all. Good night.
Thank